air-driven, but coagulation driven. So we tried to do a test to see whether we could reproduce these results, and we have this possibility in PCOB in the Northern Production Unit. We did this on module 5, and there we set 3 pressure values. We went to 5, 5.5, and 6.5. And this graph is actually composed because of the 24 samples we took. So that's a really important aspect of testing on PFAS, and in this low level concentrations, you have to do a lot of sample to get reproducible results. What we got here was that with the high pressure, that the increase, there was an increased removal for PFOS, and that for PFOA, the air concentration did not seem to have an impact. So the results are somewhat similar, in line with previous findings, but we realized that we have to test this more, and we'll be testing this again in the near future. Another way to ramp up your air injected is by looking at the saturator maintenance. We have had some saturators in Walum, which were running for 9 years. We didn't clean them, and we decided to clean them. And when you open up such a reactor, that you see initially, these are the Raschig rings that you put in. This is what it looks like after 9 years. So they become dirty, and we realized that a lot of rings were really dirty. And then we did a measurement as well, and we saw that indeed there was a difference between cleaned or fresh and dirty, and this was about 7.5%. So we realized that the cleaning frequency should be ramped up. 9 years is clearly too long. So we'll repeat this test in fall as well. And then we did another test, and this is a test on Paccal dosing, because from literature we know that Paccal dosing has a severe effect on PFAS removal. And we did that in Walum and in Notmer. We do 2 runs. We're planning more runs with different temperatures in the near future. And what we saw is that the Paccal dosing, which varies between 0.5 and 3 milligrams aluminium per liter, that this has a clear effect on PFOA, but not that much on PFOS, because apparently PFOS is already good removed through the presence of the air. We saw a big difference in Walum and Notmer. Walum is the one with less air, and you see that the full effect of the Paccal dose is not present. You have a plateau forming here, and even you have a decline in efficiency here. And this is something that has an operational value, because in summer periods we sometimes really have to dose this 3 milligrams per liter, and we do see some increased levels in finished drinking water during summer, and this might be a reason for these increased values. So conclusion here is air is critical, so work at air first, and then think of increasing the pack dosing. What we know is that pH, in our belief, has a significant impact as well. So these are also tests that were performed only once. We have to repeat them, but there seems to be an effect on PFAS removal on both PFOA and PFOS when you go to lower pHs. So this is the effect on the coagulation, flotation process. We also see similar effects on GAC, where especially in winter at high pHs above 8, we see desorption on GAC on several occasions. And this is really worrisome, and that's something that we have to understand better. In the future, a trade-off will have to be made between efficiency of pH dropping and Paccal dosing. Of course, both have an important cost impact on the apex. So when we go to conclusions, I think we can tell that DEF provides a measurable PFAS pre-removal. We see that PFAS is removed in a wide range between 15 to 65%. We should try to limit this range and to go for a more robust process. We see the PFOA removal is 10% and is actually limited. So DEF should be viewed as a pre-treatment barrier and not as a standalone solution, but it helps the downstream processes. We also concluded that all PFAS are not equal. PFAS is significantly better removed than PFOA, and PFOS shows a strong response to DEF optimization. Air concentration is the key driver and should be optimized first. There is a substantial variability in removal efficiency. So this is clearly a multivariate process, strongly influenced by raw water composition, sampling, analytical, and operational conditions. We have shown that there is an important effect of PECL dosing and coagulation, that pH adjustment might be a relevant tuning parameter. You should bear in mind that the temperature impacts DEF performance in the summer, and maybe in high temperature or warmer regions, DEF would be less affected. And the conclusion clearly is that DEF must be integrated in a multi-barrier strategy. It reduces PFAS load. We remove about 1/3 of the total amount of FSA4 removed by our total plant. And it stabilizes downstream GAC processes. So DEF optimization is inherently multivariate. Performance varies with PFAS composition, the water matrix, and process conditions. And what we have learned is that repeated testing is required to distinguish real trend effects from analytical and operational variability. So I must thank the student, Sander. He's a master in chemistry, and he did some very fine work on the data analysis and the organizing of the testing days. And of course, many thanks to my colleagues of the lab and of operations. And finally, thanks to Luc van Lokeren. He's the lab manager, and he's been a true partner in crime during this ongoing research. So I'm happy to take any questions. And
great,
just
Sven.
Within time.
Yeah, you're perfect. Thank you so much. Great presentation. Appreciate all the work you and your team did, and appreciate you sharing with us. We do have a number of questions, so we'll get right into it. How did you determine removal with the PACL dosage for a continuous process? Is the PFAS concentration consistent?
No, incoming PFAS concentration is not consistent, but you must be aware that one of the 4 graphs we've shown is represented by 40 sampling points and analytical results, and you respect the lag time of your process. So you take multiple samples throughout an experiment of maybe 10 hours. So it's quite an effort doing that. We are thinking that it might be better that you use continuous sampling to get maybe more stable results, influent and effluent, and then take a kind of collective sample instead of individual hand samples. This is something that we are thinking of that might improve the results you get.
Okay, next question. Do you have any thoughts on why foam fractionation is more efficient for PFOA versus for PFOA? Is it possibly bubble size or concentration?
Okay, I'm not aware of I'm aware. I always regard DEF as the little brother of foam fractionation, but I don't know, foam fractionation, are there polymers used in the process maybe, and this could change the the results is something that you find in literature that could increase performance of DAV as well. But then you run into the problem that many of these cationic polymers which are used are not always, permitted in drinking water applications, and you don't want to use too much polymer. So that's
but you
maybe
in
that's
terms
the
of
reason.
but in terms of your work, any theories on why the DAF does better for PFOA? Is the concentration
Well,
higher? Is it coming
the
in?
DAF does better for PFOS because of the hydrophobicity, because of the hydrophobic character of it.
Got it. Okay.
That's what we esteem that is the process behind it. Yeah.
I don't know if you've done any cost comparison. This could be a lengthy answer, but have you done any cost comparison of the
Air is cheap. No, we made a comparison between air, ramping up air injection for PCO2 side, and this was about 20,000 euros on a yearly basis. Let's say that's about $20,000. When you look at the typical coagulant dosing, it's about 200, so it's tenfold. So if you have to increase it, that will cost a lot of money. And same for sulfuric acid dosing and caustic dosing, because when you go to a lower pH, you have to increase it later on, so you pay double for the chemicals, and these costs are even higher. So they may be around the 300,000 on average for PCO2 revamp. Yeah.
Thank you. Yeah. Did you do any sampling of the residuals for PFAS?
Yeah, we did. Well, of course, we did sampling of the sludge, of the DAFs, and yeah, we have very elevated sludge concentrations, containing PFAS, and that's why we had to change the residual management, because initially this sludge was reused in large building. Development of roads and dikes, and now it's incinerated. So it costs us a factor of 3 more than it used to do, and it's not a nice application. Yeah.
Okay, I'm gonna take liberty here and just make sure we get these questions answered. We'll get to Monica as soon as we can, give her full time. But next question is PFAS removed by DAF managed in the air downstream? Is it captured in the air discharge using vapor phase GAC? Any operational exposure concerns?
Oh, good question. No. These are open reservoirs. We think that PFAS accumulates in the sludge, and when the sludge maybe has too long retention time, it dissolves back into the water too. So I'm not sure there is much exposure of PFAS through the aeration of the DAF.
Yeah, we're going to have some. I'm just going to mention we have a presentation by Christina, EPA. She has some data on foam, and I do think there is an exposure issue with the foam that needs to be sort of looked at. But thanks for that question, Chad. We've got 2 more questions. I'm going to wrap this up. What's the fate of the PFAS that ends up in the foam? What happens with the foam? I assume it ends up in your thickening, dewatering process. Where is it going now?
Yeah, we have a thickener. We have a thickening process, and we have also sludge treatment, a dewatering process. So this is a continuous process, and these the sludge is disposed in an automated and continuously way into trucks, and then it leaves the site. So,
and ultimate disposal currently is where? Where do you send it now?
It's incineration.
Incineration. Yeah. Okay.
Yeah.
Great. Yeah. And the last question about air emissions you kind of covered. And the person who asked the question about, I think it was Christine, about the residuals levels, I can follow up with Sven, or you can directly, and we can get that data to you.
So I can send her an analytical report. It's quite interesting, and it's, of course, it's of course important because we recycle water from residual waste streams, and you really have to have a measuring program to have an idea what is happening there as well. And in the future, we might have to treat them, but now the focus is on the main process and try to get this optimized as much as possible.
Well, with that, we're going to thank Sven. Thank you also for joining us from Belgium. Really appreciate your involvement with this, Sven. And we know it's late in the day there, so we know you're not going to be out with us for the rest of the day, but really appreciate your time and energy and all the good work that you and your utility did. Super exciting, and anybody who's got DAF or thinking about a settling process is going to be will benefit from what you shared.
Yeah, and Albert, really thank you for the invite. I would really like to become a member of the US PFAS community, because there is so much we don't know and so much to learn from each other, and I think we can only tackle this together. So that's what I'm looking forward to.
Absolutely, we'll make sure you get connected with all the right people. Thank you, Sven. We're gonna turn our attention now to Monica Dodson from OWASA and Orange Water and Sewer Authority in North Carolina. So welcome, Monica.
Thank you, Albert. So yeah, Monica Dodson. I'm OWASA's Deputy Executive Director, and I'm excited to be here today to talk to you all about, we've done a lot of work with PFAS, but specifically today we're going to talk about our optimization work through our use of powder activated carbon to reduce the PFAS concentrations in our drinking water. So I have been with OWASA for 22 years. My current responsibilities are leading our water resources, distribution and collection, wastewater management, and engineering divisions. PFAS is impacting all areas of our operation, so it's a big part of our responsibilities now. Again, we're only going to talk about a small portion of this, our optimization work, so I do encourage folks to go to our website, wasa.org. We've got a lot of information on there about some of the additional work we're doing. So just a little bit about OWASA. We're a non-for-profit public agency. We have about 23,000 customer accounts. We serve about 86,300 people in the communities of Carborough and Chapel Hill in North Carolina, in southern Orange County, which includes University of North Carolina, Chapel Hill, Tar Heels, which is our largest customer. We have about 151 OWASA employees, and our vision is to be our community's trusted partner in clean water and environmental protection. Just a brief overview, operational overview for us. So we have two main water supplies. University Lake is our smaller water supply, 450 million gallons of water. It was built back in the 1930s as our original water source, and then as the community continued to grow, it wasn't enough water to meet the long-term needs of the community. So we built Cane Creek Reservoir in the late 1980s, and it holds 3 billion gallons of water storage. So it's our main water source. We also have a quarry reservoir that's currently an emergency source. It holds about 250 million gallons of water, but it is actively being mined, and we're expanding that. So the goal is by 2035, we'll have an additional 2 billion gallons of water supply for our community. And we also have access to a regional water supply. It's called Jordan Lake. We don't have a direct intake on that, so we would access that water through mutual aid agreements through our utility partners and neighbors. We have a 5 million gallon per day allocation to that. We have one water treatment plant, which I'll talk a little bit more about here in a minute. It has the capacity of treating 20 million gallons of water per day. We're averaging about 7 million gallons of water per day. And then we have one wastewater treatment plant, capacity of 14.5 million gallons of water per day, about 7 million gallons per day is where we're averaging. And then we have a reclaimed water system that supplies the majority of the University of North Carolina's non-drinking water purpose needs. And then we have emergency interconnections with our utility partners, City of Durham, Town of Hillsborough, and Chatham County, which are really important. So our treatment plant, current treatment plant process is what we would consider to be just a conventional treatment process. We feed powder activated carbon. Historically, we've used that for removal of taste and odor compounds and reduction of organics. Some utilities feed that directly at the reservoirs. We feed that here within our mixing system as the water comes into the plant. And then the water goes through one of two clarification processes. So we have conventional settling basins, which were a part of the original plant. And then in the 1990s, when the plant expanded, we added super pulsators. And that's really important because you're going to see a slide later that's going to talk about, in our work, we found a difference in the ability of those settling processes to remove PFAS concentrations. Our water then goes through conventional settling or filtration. We don't have granule activated carbon, so just standard anthracite, then through disinfection and then storage and out to our customers. The solids that are collected from the treatment process go through dewatering. We have filter belt presses. Those they're dewatered to about 25% solids. And then currently about 94% of that's going to composting and about 6% goes to the landfill. That's another area we're making some changes. And again, I'll talk about that here in a minute. So our water quality, this is important just to kind of, we wanted to highlight what this looks like on an average and maximum basis. With powder activated carbon, some of the biggest competing factors are your organics and your taste and odor compounds. So we average around 5 to 6 milligrams per liter on our organics. And then MIB and geosmin, around 40 nanograms per liter. But we do see at times during the summer when algal season is active, those can peak up to 100, but not something we consistently see. We have had an active PFAS monitoring program since 2018. We have expanded that program over the years as we've learned more information, but in 2018, we started monitoring our raw water supplies, University Lake and Cane Creek, and our drinking water, and then we did take some initial samples on our wastewater influent. Through this work, we have identified that Cane Creek Reservoir is our main source of PFAS concentrations in our drinking water. Through some additional investigations, we monitored the tributaries of the creeks that are feeding that reservoir and found that previous land application practices from another utility was the source of that contamination. We also do, because there are PFAS concentrations, so Cane Creek Reservoir is our major source. We found little to no concentrations in University Lake, our other reservoir, but as I mentioned earlier, it's smaller, so it's not something that we can rely on solely to meet the community's needs. Because there are PFAS concentrations in the water, we did test the fish and found, unfortunately, high levels of PFAS concentrations in those fish and worked with our local state and health departments to issue a recommendation not to consume the fish coming from that reservoir. And then we're doing some work to understand our wastewater concentration. So what's coming into the wastewater plant, where there are opportunities to reduce concentrations. And then we routinely monitor our influent and effluent wastewater as well as our vital solids. But again, we won't talk about more of that work today. So this, as you can see, the concentrations, not sure folks on the call what you typically see in your areas, but for North Carolina, the concentrations of PFAS in the Cane Creek Reservoir are pretty high. From the state's perspective, it's one of the highest reservoirs in the state. And so as you can see from this graph, the green bars are, and we're going to just focus on PFAS and PFOA. This is what the concentrations are in the raw water, and then the blue bars are what's in our drinking water before we started implementing some optimization efforts. So as you can see, powder activated carbon was reducing the concentrations, but wasn't fully removing them. And so we engaged with a consultant to start to develop a planning study for OWASA's holistic response to PFAS with the goals of protecting the public health and the environment. The first task in this was to look at our drinking water and what could we do immediately to reduce the concentrations in drinking water, but also look at what would the best long-term options be for our drinking water, and to develop a plan to better understand our wastewater and biosolids and what the future looks like in that area. So again, this presentation is just going to focus on our optimization work. So the optimization work first started with bench scale testing. So we looked at 5 different powder activated carbon products through jar testing to see how they performed. We looked at different blends of University Lake and Cane Creek water. And then we took the best performing products and put them through some additional jar testing. Those included optimizing the dose and then evaluating detention times. And then from there, we then started to implement full-scale plant studies, which we'll talk about. So these are just brief results of our bench scale testing of the the 4 different products that we looked at. Again, just looking at PFAS and PFOA, that black dotted line is what our source water concentrations were before removal. And then each one of those bars represent each one of the different products that we tested. The Jacoby product, the light blue, is what we were using at the plant at the time. And then the Calgon product was a product that we had some information on that performed pretty well. And then the ADA, which has now been renamed to ARQ, had a product on the market, and they also had a product that they were testing. So we tested both of those from the bench scale perspective. And so as you can see from the results, the Jacoby product that we were currently using was one that was less effective, and the Calgon and ADA products were a little bit more effective. So we moved those into the next round of testing and started looking at, like I mentioned, dose optimization. And what we found with dose optimization is, as you would expect, the more powder activated carbon we fed, the more reduction that we got. But we did notice that about 45 parts, we did start to get some diminishing returns. So the removal plateaued essentially. And to be able to get below the detection limits, we had to feed around 100 parts, which wasn't feasible. We also found that in our jar testing that it didn't seem like detention time had much of an impact, but from a plant scale perspective, we have found that detention time does impact PFAS removal. So then we moved 3 products into our plant scale testing. So I would say that the Jacoby we were already currently using, we did test that at our normal, before we started feeding PAC to try to reduce PFAS concentrations, we averaged around 15 to 20 parts per year, parts per million throughout the year to be able to remove taste and odor compounds. And so we started to just turn that up to eventually up to 45 parts to see what kind of removal we could get. So if you, just to kind of orient you with this graph, PFOA is the blue line, PFAS is the green line. And so for the Jacoby product, we were able, at 45 parts, we were able to get full removal of PFAS, but we weren't able to get full removal with PFOA. And then we started plant scale testing the ARQ product. We just used a product that was currently on the market. It did really well. At 25 parts, we were able to get below with PFAS, but not with PFOA. But when we turned it up to 35 parts, we were able to get no detections on both of those compounds. The challenge with the ARQ product was that it stayed suspended, so it didn't fully, we had issues with it fully settling in the settling basins. And so the issue that was causing was when we would turn up the plant flows, we would start to get some solids filtering over into our filtration process. So we stopped the trial on that, and then we moved over to the Calgon product. So the Calgon product, we were able to feed up to around 35 parts and start to see detections below the MCLs. That purple box that I have highlighted there, that's when OWASA was doing our pilot testing on what our long-term strategy would look like. So the way we had to set up the pilot allowed some PFAS, untreated PFAS, to be able to make its way through the process. So those results aren't completely representative, but when you look past that, you can see we were able to get below the MCLs. So we then switched over to the Calgon product because the product, this was really the only product on the market that meet the objectives that we were trying to meet with our treatment needs. We went through the sole sourcing process to be able to use that here at the facility. I will say that we are still continuing to work with the ARQ folks to improve their product. We're actually going to shift over to a pilot scale here pretty soon to see if they've improved that settleability. We're averaging around 30 to 35 parts of powder activated carbon to be able to get that PFAS removal, as well as our taste and odor and organic reductions. And then, so the downfall with using powder activated carbon as your source for PFAS treatment is all the PFAS ends up in your residuals, in your treatment plant solids. And so we produce about 750 tons of solids per year, so about 150 truckloads of this truck here that you see. And the concentrations of PFOA and PFAS are highlighted here. So about 125 parts per billion of PFOA and 180 parts of PFOS. And so what we're doing now is we're shifting all of our disposal of these solids to 100% land application. We're going to start that in actually this coming up month. So this is a graph of, our overall performance. So as you can see, we've been consistently below MCLs since we've worked to optimize our process. We do monitor these on a weekly basis. So we have seen, as we're making some changes to the process, we've seen some exceedances, which again, I'll talk about here in a minute. But overall, PAC's done really well. I mentioned earlier the differences between the settling pulsators and the conventional settling bases and the super pulsators. So this is a graph looking at PFOA and the concentrations coming out of each one of those settling processes. And as you can see, with the exception of one sampling event, the settle pulsators remove the PFAS to below, or PFOA to below the MCLs. And very rarely do we see that with the conventional settling basins. And here's the same results for PFAS. And again, no detections from below detections with our pulsators. And then we've seen some instances where we've been able to get below that with the conventional settling side, but the majority of the side, it's above that. So for folks who know about these different settling processes, the settle pulsators have a suspended blanket. And so the water comes through the bottom of those tanks through that blanket. So you have a suspended solids blanket in there. And we think that's the reason why it does so much better, is you have that opportunity for it to kind of essentially act as a filter, where with the settling conventional basins, if the product settles well, those can settle pretty instantly. So that's where your detention, it's related to that detention time. So for WASA and our next steps, we are continuing to optimize our use of powder activated carbon. I mentioned to you that we're going to retest the ARQ product. We're also continuing to collect information as we make changes to the treatment process. So one of the challenges for us is we take those pulsators down twice a year for cleaning. And so we need to come up with some different operational strategies during that cleaning time to avoid PFAS making its way into the drinking water. So what we'll do during those times is likely pull more water from our other water source, University Lake, to reduce those concentrations. We do a lot of monitoring. We're internalizing our PFAS monitoring program. So currently we use contract labs where I get instrumentation so that we can start doing that in-house, which will really be helpful. Our pilot study showed that granule activated carbon was the best long-term solution for us. And again, a big reason for that is that PFAS will be captured in that media that then can be sent off for regeneration, destructions associated with that, and then that media can come back and be reused. We do have in our CIP planning to begin design and construction of that facility. The timing of that is something we're still trying to work through. I mentioned earlier, we're doing a lot of work with trying to understand wastewater biosolids and impacts there. So it may be that we need to focus some more of our efforts on some upgrades within those facilities to reduce our impact, since we are currently meeting the drinking water standards with powder activated carbon. But hopefully over the next year, we're going to have a clearer plan of what our long-term path forward is for our overall response to PFAS. That is all I have, and I'm happy to answer any questions you all may have.
Thanks a lot, Monica. Great presentation. We do have a couple of questions. For the ultimate disposal of the PAC currently, is it landfill or is it land application, like farms or landscape material?
It is, yeah. So for the water treatment plant solids, it is landfill. I may have said land application, but it's landfill.
No, you said landfill, but
okay.
they just wanted to clarify. Yeah, so
Yep,
you're going to landfill, and okay, that's great. And do you have any I don't know, just to follow up, any costs? I don't know if you know that off the top of your head, costs per, I don't know what it is, per ton or for disposal.
Yeah, it's gonna cost us an additional about $160,000 per year. So I mean, in the grand scheme of things, not a significant increase for us. It's more of it takes a lot more time. The landfills are a little bit further away, takes a little bit longer to be able to dispose of them there. So it's really some staff time that's not captured in there. But yeah, about $160,000 increase per year to be able to do that.
Okay. And next question is, how often do you monitor PFAS for influent effluent?
Influent effluent on our wastewater would be, we do that on a quarterly basis.
Okay. How about the water plant?
For the water plant, right now we're actually doing weekly testing of that, because we're doing some special studies just to continue to learn about the PAC's performance.
And then do you have any pack dosage adjustment guidance, SOPs for operators?
Oh, that's a good question. Those are still under development. So it's one of the reasons why, like I said earlier, we're doing weekly sampling and just seeing how those concentrations can change. Like I said, we've learned that when we take those pulsators down for cleaning, we need to have a different operational strategy. So yes, those are definitely things that we're working through.
Okay, next question. Do you know the detention time in the mixing and clarification basin at your plant?
Yeah, so it depends on flow, but based on our average 7 MGD, it takes about 8 hours for the water to get through the conventional settling basins, and it takes about 4 hours for the water to get through the superpulsators.
Okay, next question. Are the influent effluent samples grab samples or composite samples?
So and when I think of influent effluent, my mind always goes to wastewater. So for wastewater, they're composite samples. For the treatment plant, influent effluent, it's source water and drinking water. It's grab samples.
Okay. And then with all the sampling that you guys have done, have you been able to identify any sort of hotspots or the sources of the contamination? Is there any work underway to curtail or cut back or eliminate the whatever's causing those levels?
Yeah. So we did the creek sampling. We found some of those creeks had concentrations that fed the reservoir and some didn't. So as we then started to work our way up the creeks to see where was it showing up. And so it clearly showed that it was land application from another utility. They hadn't applied in years, but we did work with them to remove those fields from their program. The challenge with that is, from a land application perspective, being able to identify the extent of the contamination, and how deep is it in the soil, how much of the land is affected, is it affected by, did it make its way into the groundwater, is that infiltrating into the reservoir? There's just so much work that would have to be done to try to determine that.
Yeah.
These are that aren't owned by Awasa, they're privately owned, but we have communicated that information to the state. We have communicated that information to the counties in which those fields are in, and so it's definitely something on the radar. As those opportunities to be able to find ways to identify and remediate. It's certainly on those folks' radar, and of course, Awasa is here to support any future work that may happen. What we found was it's going to be, and it could take decades to be able to remediate that. So we just found it would just be better if we just put treatment here at the facility instead of trying to focus those efforts out there. But certainly something that's still really important.
Okay, and then I don't know if you've found any other. The question is, have you found any surrogate parameters for evaluating PFAS removal? I don't know if you've looked at that at all.
Yeah, we haven't. We are working with there's a North Carolina, and all states do as well. We have a really great research community, so we're working with NC State and UNC and some other folks, Duke University, to try to expand methods and identify opportunities to be able to do that. They do have a method at NC State that looks at PFAS precursors, so you may not. It's a neat method that lets you look at essentially all potential PFAS concentrations versus a lot of the sampling that folks do now, including us, focuses just on those 40 samples that the contract laboratories can identify. This method lets you look at all concentrations, and it gives you an idea of what could be transforming into these, these PFAS and PFOA, these other compounds.
Great. Yeah, thank you very much. And just wanted to, again, thank you for your support of the commission. Back to Sven's point about how we need to help one another. Monica was incredibly helpful to share her experience with the commission, and that is super helpful when you're looking at some new ideas. You know, what have people done? What are they finding? So just want to make that thank you to you, and thanks for presenting today, and thanks for getting all that good information in a compact 20-minute presentation. Thank you so much.
Yeah. Yeah. Well, we appreciate the opportunity. Please feel free to research us and reach out. Happy to answer any other questions people may have.
Thank you so much. All right, so we're going to move on. Our next speaker is Christiana Hop Jones. She's with American Water. And just so you know, Christiana, you have your full 20 minutes. We're going to back things up a little bit. So welcome and thank you for being here.
Awesome. Thank you so much for having me. It's a great opportunity to talk about PFAS in such a great group of all the different experiences that people have had with implementing treatment. So I want to talk a little bit today about some of the experiences we had. We have a very extensive PFAS treatment media pilot testing program where we've run over a dozen pilots to date, and I want to highlight just some of the insights and some of the lessons learned. So we'll be looking mainly beyond PFAS removal. We are fully aware that the moment that you put any sort of treatment in, there may be some operational impacts or some media aging that may be happening. Talking a little bit more about the removal of organics and backwash water quality when it comes to PFAS. But let's jump right in. I want to first talk about our first surface water pilot that we've conducted, which was at our Canoe Brook treatment plant, which is a 23 MGD plant with a surface as well as a groundwater component. The pilot that we established there was conducted only on the surface water side, downstream of the filter effluents. One thing I want to highlight here as well, so this is a DAF plant, and the coagulant that's being used is aluminum sulfate. And most of the times you learn things when things aren't going to plan, and this is exactly what happened here. So about 4 weeks after starting the PFAS pilot, our pilot media fouled very quickly. So this graph here shows the head loss for one of the ion exchange resins. And what caused the fouling, we kind of needed to figure out. We were able to backwash GAC and novel media. And for our ion exchange resins, we tried different protocols, different cleaning protocols. We tried hydrogen peroxide soaks and cleaning protocols for the gel type resin and for the macroporous resin. We first tried chlorine, then hydrogen peroxide, and then backwashing. Whether we were successful or not, well, that kind of depends on the media. Well, the GAC medias did recover after backwashing. The novel media did see some recovery after backwashing, but the media itself was compressed into, or some of the media was compressed into chunks, and we were unable to break that up. And then the chemical cleans that we performed on the ion exchange resin did not really sufficiently lower the differential pressure. While backwashing was more successful in this, the resin really fouled quickly again. So what caused the fouling in this case was, so after an autopsy of the ion exchange resin, we saw that it was so basically our coagulant that made it through that caused the fouling. So we kind of, in this case, because we were at the beginning of the PFAS pilot, we decided to restart the whole pilot, and saw much better success after the coagulant dose was optimized there. I do have a few other things I want to share, so I'm going to be switching around a little bit, talking about a few other treatment plans to talk about other operational impacts. So 2 other treatment plants in New Jersey are Raritan Millstone and our Canal Road plan. Both receive water from basically the same source, which is indicated on the right-hand side in very similar PFAS as well as TOC concentrations. The differences are that the Raritan Millstone plant is a conventional treatment plant with free chlorine being added into the sedimentation basin and through the gravity filters, while Canal Road includes pre- and intermediate ozone. So when we established a PFAS pilot, again, in both cases, we established that pilot after the gravity filters. We can compare kind of the backwash frequency. One thing to note here, because at Raritan Millstone free chlorine was added ahead of the filters and the free chlorine concentration was still too high for some of the ion exchange resins, we dechlorinated the feed going into the pilots. And so the little asterisk here shows which columns received dechlorinated feed water. So what we so if we look at the backwash frequency here, every line on these graphs is a backwash cycle. And so you can see that, first of all, we have from our cleanings at Canoe Brook to trying to get the ion exchange media once we had a higher differential pressure going through to revamp that again, and we were unsuccessful with our cleaning protocols. We decided in both of these cases here that we would backwash all resins as a standard practice. I know that's not necessarily what the manufacturers suggest, but that was the only way that we thought we could move forward. Within the first 2 months, we could not maintain our anion exchange resin differential pressure below 4 psi, and therefore couldn't recover that level post backwash. So we decided on the RM side to kind of to continue testing and keep trying, but we had huge issues with the ion exchange media on that, most likely due to biogrowth. And I'll talk about that in a little bit. As you can see that between the novel media and the backwashes on the RM and Canal Road side, they were fairly similar. And then there's a difference also in terms of backwash behavior between the GAC that saw dechlorinated feed compared to GAC that just saw the chlorinated feed. And again, I'll go into more details in that in my next slide. So let's look briefly at the before results, the removal results that we've seen on the same media in comparison for both of these plants, so RM and Canal Road. And from the left to the right, we have GAC, ion exchange, and novel media. The dashed line here is Raritan Millstone, and the solid line is Canal Road. So generally speaking, the GAC and novel media for both of these sites compared well with one another, and we didn't see, in terms of performance, not a huge difference, but you can clearly see the difference in the ion exchange media. Again, we're assuming that there's fouling, and particular biofouling happening here, so that clearly dechlorination would not be a good strategy for ion exchange usage in or at a Raritan millstone. So let's go a little bit deeper. And so what we conducted is, after every pilot, when the media was evacuated from each of the columns, that we took samples from the top, middle, and bottom of each of the columns. And so One way to look at media aging is to look at the ATP results that give us an idea of the amount of biofouling that we see on the media itself. So on the top here, I'm showing the GAC and novel media. In red, the top part, where we took some from the top part, green the middle, and then blue the bottom. And as you can see, that the GAC that saw chlorinated water is that we saw a lower ATP results in that top layer, but at the middle, as well as the bottom, that those results were comparable to any sort of GAC that didn't see any chlorinated water. So for the novel media that saw the chlorinated influent, we did see that the chlorine kind of made it all the way through, then showing in ATP results that were low throughout the whole column. And now a GAC column that saw dechlorinated water, we saw that at the beginning or at the top layer, as well as the middle and bottom, the ATP concentrations were up to a whole order of magnitude higher in that. So really suggesting in this case that there was higher amount of biofouling going on there. If we look at the ion exchange media, again, we didn't test chlorinated water on the ion exchange media, so no results here. But if we look at the difference between dechlorinated and non-chlorinated water, we can clearly see there as well, for the most part, that we saw higher amounts of ATP in the dechlorinated water, suggesting higher amounts of biogrowth in the ion exchange media, which again is confirmed with our operational parameters as well. I do want to spend a few minutes on organic matter removal. We decided to run TOC throughout all the columns, but we also decided to try to understand a little bit more about the type of organic matter that is being removed by the different medias to see if there is a difference. So for that purpose, we ran excitation emission matrix plots. So this is where you measure the fluorescence of the organic matter coming through. So we did that for the pilot influent as well as the effluents of the different columns. And what you get is this little 2D plot that will indicate a little bit more the type that you see, whether it's fulvic acid-likes, humic acid-likes, or other microbial product-like compounds. So we use these plots to kind of look through the media performance on the GAC side. And so if you compare on the start, so whenever the GAC media was fresh, you can see that's very little of TOC that actually made it through. On the right-hand side here, I'm showing the breakthrough curve for TOC removal as well. But the plots, the EAMS plots, kind of show that there is really no predominant fulvic, humic, or microbial organic matter matter that made it through. At the end of the pilot on the GAC side, we do see that fulvic acid peak growing as indicated by the plot on the bottom. If we look at this for ion exchange, we can see that after about 7,000 bed volume, that there is still some removal of organic matter, but not nearly as much as we saw on the GAC side. And after about 109,000 bed volumes, we can clearly see that the makeup of the organic matter going into the ion exchange column as well as coming out is almost identical. Indicating that there's very little to no TOC removal anymore. If we look at the novel media, we can see that at the beginning as well as at the end, that the Eames plots look very similar to the pilot influent itself, really highlighting the case that if the installation of PFAS removal should also have for any particular treatment plant any additional organics removal, then novel media would not be the one to choose in that case. So clearly, no additional TOC removal when looking at the novel media. I very briefly want to talk about the backwash water quality as it pertains to PFAS. So we did measure at the end of each pilot, we backwashed each of the columns and captured as much of the backwash water as we could to compare it to the water that was going into the pilots. So on the left-hand side here, you can see that we have the pilot influent as well as the GAC and ion exchange and the novel media. The color pattern, again, in blue is PFOA, red PFOS, and then the rest of the carboxylic and sulfonic acid. And as you can see that at our Canal Road site, we did not see a difference in the makeup of the PFAS in the backwash water compared to what was going in, really suggesting that there was no removal coming from the column themselves, nor that there were any fines that were in the backwash water in this case. Now the story looks a little bit different at our Raritan Millstone plant. Very similar as the Canal Road for GAC and ion exchange, but on the novel media side, we can see that the TSS at 60 milligrams per liter, A being higher. So what we think happened here during this backwash is that there were fines that were coming out through the backwash cycle, which still had PFAS attached to it, especially the very hydrophobic ones, PFAS in this case. Also shown on the bottom graph, the long chains were the most dominant one. So clearly on the backwash side, depending on what the pre-treatment is like, there may be more PFAS in the backwash water because of the fines than when you use novel media compared to others. So a few takeaways here. It's important to do these pilot studies and look beyond the PFAS removal for each of the different medias that are out there. We think it's a great opportunity to learn and identify as early as possible some full-scale challenges that will only benefit when implementing the PFAS treatment on the full scale. As I've shown as well, the upstream treatment process can have a substantial impact on the media performance and on fouling. So it's really important to optimize that before the treatment is being implemented. Biogrowth needs need to be mitigated to make ion exchange viable for surface water sources. I think we've seen other talks as well where ion exchange in surface water, that there are struggles there. So, backwashing was helpful, but not nearly as much as we would have liked to see here. And with that, I would like to acknowledge many of the folks that were running the pilot, Smart McDonald's as our partner on the consulting side, and many New Jersey American as well as American Water folks here. And with that, thank you for your attention.
Thank you, Christiana. Yeah, we're going to go right into questions. And so the first question was, how high was the backwash rate used for the ion exchange?
How high was the backwash?
The backwash rate, like, I don't know, the hydraulic loading rate,
I
per square foot, maybe.
If Margie Gray is on, if she wants to answer that. I wasn't there, so I didn't backwash it by myself. So
no problem. Yeah, we can, or you can put it in the chat. But yeah, if Margie's on, you can come off mute. But next question was the backwash rate determined by the manufacturer or based on bed expansion?
Okay.
So again, it's another backwash one. I will defer to Margie here. I know
No
that
problem.
that we try to go very gentle on the ion exchange media in those to avoid mixing of the media as much as possible. So it wasn't the same rate as what you would do on a GAC or novel media side. So we try to really just fluff the media more than really do a full thrown backwash here.
And do you think ion exchange would be applicable in a gravity filter?
That is an interesting test. We tried to do that a little bit, but we couldn't keep in our PFAS pilots. We couldn't keep the right parameters for a gravity filter going on the ion exchange side, so it would foul just too quickly there.
Okay. Next question is, has there any research been done on the effect of pH shifts, increase or decrease in the media when starting up ion exchange in the presence of aluminum coagulant? Could it promote clogging? Would there be a target aluminum residual concentration or pH after gravity filtration for that post-filter ion exchange?
So we have not, I think, looked in detail on the change of pH through ion exchange media. Was a little bit above the scope here. Like I said, I think there's probably a lot more research out there already, but we didn't conduct anything else on that end.
Okay. All right. Next one is regarding media aging section of the presentation. Any suggestions why dechlorinated feed would have higher ATP than unchlorinated feed?
At this point, no. I don't know whether the bugs really like the addition of the bisulfite that was used, or thiosulfite. I don't quite know what we used as the chlorination agent. We only had one site where we tested that, so that kind of is shown there that our N is relatively small. So would be careful with necessarily overinterpreting that. But no, we didn't do any further studies whether we promoted necessarily growth here through that biofouling, through dechlorination, or if we promoted growth of any particular bacteria or group of microorganisms there.
Okay, and last question. On the one slide, you were showing the percent removal of PFAS against bed volumes, and it looked like the novel absorbent did better on a bed volume basis than the GAC. Was that your conclusion? You mentioned that they're similar, but it looked like the novel absorbent looked like it was
So
it
yeah,
did better.
so the bed volumes treated there were higher, but I think it all depends a little bit, similar to ion exchange media, that what are the bed volumes that you need to go even with GAC. So it's not necessarily a one-to-one comparison in that. So it's not 1,000 bed volumes on the ion exchange or novel media equals in terms of cost 1,000 bed volumes on the GAC side. So while yes, in terms of bed volumes, it did perform better than GAC, so did potentially ion exchange, but that doesn't necessarily make it the better option in terms of cost.
Yeah, I'm smiling because that's been a perennial major aggravation of mine of people comparing bed volumes. And it's like, well, if the bed volumes themselves are different, then we're not really comparing the same thing. So thanks for clarifying that.
Yeah.
And yeah, good job to all of your work, and thanks for sharing this. I do have a little bit of information about Canoe Brook in my presentation that you might be interested in a little bit. So Thank you very much, Christiana. Thanks to American Water for sponsoring you and allowing you to present. Thank you, and we'll look forward to talking later. So with that, we're going to invite Jim Muller to present from Passaic Valley. Welcome, Jim.
Thank you. Can you see my screen?
Yeah, everything's
Albert?
good. Yep.
Okay, good. So pleasure to be here today, and nice job to the prior presenters in terms of all the great work that's been going on both yesterday and today. So it's a pleasure to be here with y'all. So I'm going to talk today about our Little Falls water treatment plant, the PFAS assessment and pilot program that we've undergone, and then the upgrade recommendations for the treatment plant in terms of where we're going. So, and hopefully did my slide advance or no?
No.
There we go. Did that move?
Now we're going.
Okay, good. So here's just an overview of PVWC's system. And I don't know if my cursor is visible or not, but the blue areas are our retail areas, these light blue areas. So it's Patterson, Passaic, and Clifton.
We can see your cursor, just so you know.
Oh, okay, thank you.
Yep.
So Patterson, Passaic, and Clifton are also the owner cities of Passaic Valley. So we were created by state-enabled legislation about 100 years ago. The prior water system was condemned, and the owner cities enabled the creation of Passaic Valley Water Commission as we know it today. So, and those are the three key parts of our retail areas, as well as Prospect Park. Also, Lodi and North Arlington are the six major retail areas either within our main system or adjacent to our main system. There's two satellite systems we have up north in West Milford. One is Highcrest and one is Postbrook. And you can see these concentric circles are basically the mile distance from Totowa, which is right in the middle, that black dot right in the middle of the map. So it goes out by 5, 10, 15. So the West Milford systems are between 12 and say 16 or 17 miles away, really satellite systems compared to our main retail areas. Our wholesale is in the green. So we have about 23 towns and utilities as wholesalers. American Water is a big customer there. Our largest wholesale customer is American Water. And then you see down here, the red areas are our interconnections, where we have interconnections with folks, emergency interconnections that we use if there's an issue with a transmission break, or a few years back when North Jersey had a problem with their tunnel and Newark had a problem with their pipelines, we use those interconnections to actually feed water to more people and help facilitate. So very interconnected system. We have two sources of water, Wanacue, which is up north, run by North Jersey District. And we have an average daily flow of about 35.5 million gallons per day. And then the Passaic River, right here down in that black dot Totowa that we take off directly from the Passaic, it's treated by PVWC at our Little Falls treatment plant. And pumped into the distribution to our three storage reservoirs, Levine, Great Notch, and New Street. And we're in the process of actually covering our first storage reservoir now, and we're building storage tanks at Levine. And that'll continue over the coming decades. So about 42 million gallons per day is the annual average daily flow from the Passaic. So it's about 77 million gallons a day total that we pump and distribute to both our retail and wholesale areas, and obviously emergencies, we can provide even more water. So that's just an overview of the system. So our PFAS data and piloting approach, this is kind of, we initiated development of a PFAS pilot work plan to evaluate post-filter granular activated carbon. So we have GAC filters here at Little Falls. At North Jersey, they do not. I believe it's anthracite up in North Jersey, but we have GAC at Little Falls. And we initiated, we knew the health advisories were out, EPA at the time, 2022, 2023. So we said, well, let's get ahead of this. We were compliant with the New Jersey DEP standards at the time of 14 nanograms per liter and 13 nanograms per liter. We said, well, let's try to get ahead of this because we know the 4 nanograms per liter is out there. It's a health advisory and will likely be promulgated soon. So we started working with Cornwell Engineering, who was already under contract. I'll go a little bit through the contractual evolution, really for the amount of dollars that were spent on this to highlight, it was no small task. But we started working with them on just a work plan. And the plant data at the time, which is this bottom right graph, you see the 4 net nanograms per liter is the dashed black line on the bottom. That's the 4. And you can see most of the data, and there's the New Jersey DEP standards at the time of 14 and 13 nanograms per liter, and the blue lines, the blue solid line and the blue dashed line. And you see most of the data, and it started coming down over time, was compliant with the state, but really none of it was compliant with the proposed new the new regs, or the health advisory at the time. What they were kind of intimating was the target of 4. So that's where we started as a backdrop of why we started to look at piloting. This is our plant process overview of it. You have the raw water intake, you have the micro sand going into our active flow process. So we have a high rate settling process. The plant was upgraded about 25 years ago. I think some of the folks on here were involved in some of those designs at MOD or some of the other firms at the time. But they used to have really big sedimentation basins. All of that was, demolished, and a high rate settling system was put in place, active flow. So went from maybe an 8-hour HRT or a 6-hour hydraulic retention time to about 20 minutes. So we really gained a lot of footprint from the active flow high rate settling process. And then you have the tube settlers. We have ozone. The chlorine gas was replaced, and with the ozonation, but again, 25 years ago. So that's TCPA, obviously, that we're under, but different kind of disinfection. It helps destroy organics, which is great as we're taking the water off the Passaic River. We have two batteries of filters, one from 1966, both GAC, one from 1966 and one from the 1980s that are still in service. During peak flows, just one note, and I'll cover this as part of the plant upgrade. Basically, all filters have to be in service. So the plant is designed at 80 MGD. Annual daily average, it's 42 million gallons per day, but it's designed for 80. Filter bottleneck is actually probably more like 75. So that's our peak flow during the summer, which we're ramping up into. At that flow, really no filters can be out of service. So one of the things as I start talking about the plant upgrade, it's even while we're looking at post-GAC filtration to meet PFAS levels, we're also talking about expanding filtration and just improve our throughput there, and that we can have a unit out of service and still make a peak flow of 75 or 80. And then we add our sodium hypochlorite, sodium hydroxide, and then it gets pumped out to the reservoir. So that's an overview of where we were. So what do we do? So when we started that with Cornwell in October 2022, we already had a $125,000 contract with Cornwell to look at corrosion control and microbiological treatment. And we expanded that work to really start thinking about PFAS, just because of the health advisories at the time. We wrote a change order to cover costs on that work plan. We also started looking at our lab operations in September of 23 in terms of our throughput at the lab, number of samples, knowing, hey, regs are going to be changing. Do we have to do all the sampling we're currently doing? And if not, maybe eliminate it. And what new sampling do we need to plan for? And it's about 40,000 samples a year, 40 to 50,000 through the lab. It's about 12,000 a month that we're processing. So just that, the analytical throughput in terms of what we needed to start thinking about. And we're still working toward certification for PFAS. In November 2023, we actually awarded a contract to Cornwell for the pilot program. So we started with a work plan under an existing contract, started getting that going. Once we had the work plan laid out, we're going to go, we had a pilot from 2019. We needed to be relocated. My maintenance folks did that. And then really wanted to staff that for a year or two in terms of running different media through it. 4 different manufacturer GAC media were piloted. And that was $550,000. We started to engage with the Water Research Foundation and wanted to do a peer review on this, which they were great. So we entered a $55,000 contract with them in February 24. And then in April of 24, EPA promulgated the new regs. So I'm just glad we had started to get ahead of this a little bit. We didn't know the regs were going to be promulgated necessarily in April. but at least we started getting ahead of it. And that really kind of heightened our look at it as opposed to just a pure pilot program. Started thinking about, hey, we got to start thinking about planning and design, because as I showed you, the plant data was not going to comply. And we couldn't just optimize our way there to get into compliance. It wasn't marginal, it was pretty significant. So in August of 24, we awarded a contract to Black & Veatch with Mott MacDonald as a kind of a super partner for $2 million for planning and design, a basis of design contract, to take the pilot data and start converting it to parameters, design parameters. Technology selection is one, overflow, empty bed contact time, different things in terms of how we're going to size that, and then look at the rest of the treatment plant and what else needs to be upgraded to accommodate this. And I'll show you that at the end. September 24, we wrote another change order to $270,000 to Cornwell for additional studies. It was driven by the WRF peer review, as well as Black & Veatch started to get involved from a design perspective to start saying, hey, how are we going to, what information do we really need to know to feed into a full-scale design, as opposed to just the research end of it. I also mentioned those satellite systems up in West Milford. We do have PFAS treatment on one of them. It's groundwater. It's a package system. So we started piloting, I think it was Dexor up there, in terms of a different technology for what we might do up there. So it wasn't just aimed at Little Falls. There was some side work we're going on to optimize what we're doing in Postbrook. March of 25, we ordered another contract to Cornwall for extended studies. So just time for sampling and extended time to look at more and more things. In April of 25, we entered a tailored collaboration. WRF had matching funds, and we were spending a lot of money, so we wanted to, again, looking at efficiency of PFAS, similar to what American Water, I think, just presented on, and in terms of the regen rate or how long it would last, and that's in process. Another change order awarded, $270,000 to Cornwell. Still yet again another equipment to purchase, and then finally another change order that we just awarded. So why did I go through all that? It's a lot of time. There's two things on here that are pretty immutable: time and money. And that's what we've invested in to get ahead even before the regs changed, and then after they changed to really adapt to how are we going to make this work? How are we going to make this real? And you need that time to get into it, and you need site-specific information in terms of how you feed that into your own design. So it's one lessons learned is this is a good way to do a program, particularly at scale. Most of the technology has been focused on groundwater. We had our own groundwater system in place, much smaller. We're surface water, much larger scale. So, how we scaled up was no small feat. So our totals to date, 2.4 million on piloting alone. Different technologies, efficiency removals, different things we're looking at there. 150,000 of that is through that tailored collaboration where WRF was kicking in 150,000. Peer review of 55,000, and then again the planning and basis design, how we're going to scale this up, another 2 million. So about 4.5 million spent to date. Again, I have a schematic toward the end. Well, I'll show you the order of magnitude of cost, but it's a $400 million program. So this is the kind of piloting and planning you got to do to launch into a realistic program. So our peer review on May 8th, we kicked off the pilot and basis design kickoff meeting with WRF and the national peer review members. And on October 22nd, 23rd, and 24th, we had a 2-day workshop on technologies with WRF out here at Little Falls to peer review the pilot program and the effort. So folks involved: Cape Fear Public Utility Authority, Greater Cincinnati Waterworks, Orange County Water District out in California, American Water, Veolia, New Jersey contingents, North Jersey District, Ridgewood Water, Aqua, and New York City DEP. My alma mater over from New York came over and participated in that. It was really great 2 days. And some of the preliminary findings, and so some of this is kind of vague because we're still have to submit this report through WRF and get it published, and we're in the process of finalizing that. But just to share, again, water for the study was diverted from the full-scale filters that I showed you, but prior to chlorination. And products from 4 GAC suppliers were set up in parallel, 6-inch diameter filter columns, and full-scale water, filtered water was provided. One of the key findings: the empty bed contact times became an issue, and this is actually a big design issue. So, the original thought was 20 minutes was the empty bed contact time target. And with that comes larger footprint, right? As we're looking at upgrades and footprint on the site. So what we found through the pilot at, in Cornwall Fund, and we provided all this data to DEP, that that might produce less efficient PFAS treatment and more frequent GAC replacement than is necessary. And the results were indicating that fouling was occurring at the longer empty bed contact times due to the presence of naturally occurring natural organic matter from the Passaic River, as I mentioned. So, at the lower bed volumes, the larger EBCTs and shorter EBCTs was a key design variable. So we're looking at maybe designing to a lower EBCT, and DEP gave us feedback on the data just a few weeks ago and saying, hey, we'd like to see your pilot that actually go pilot. So that explains some of the change orders we've written is actually to further explore that and demonstrate it, even while we're finalizing conceptual designs, and I'll get into that in a second. Keep looking at the EBCT, the empty bed contact time, as a key design parameter. So DEP wants to see more data, which was great, and it's something we're pursuing. So that's explains some of those contract costs as questions started to be raised. Had to spend more time and effort to focus on that so we could scale it up into a design. So the final report on the first phase of piloting is pending submission of work. So again, that's why I'd love it if it was finalized and we could just reference it. But it should be published hopefully, maybe by the end of the year. And then the next phase is planned at the lower EBCTs based on the recent feedback from New Jersey DEP, based on the pilot data, which is good. So here's our Little Falls treatment plan. Here's the conceptual upgrade. So this is that planning and basis of design contract that we have Black and Beach working on with Mott. In the red boxes kind of highlight the new processes. So most of our treatment, and again, if my cursor, you have the existing main pump station on the bottom of the screen, kind of bottom center. That's the existing main pump station, and the pipes coming in and out of it that take in raw water and put out the clean water, the treated water. It's about 100 to 120 years old. And a lot of those pipes are 100 to 120 years old. So even without PFAS, this bottom center was a big to-do at the treatment plant that we knew. I started here in February of 22, and we had a failure in summer of 2023 in that pump station on an 18-inch valve gave way. It's only 80 years old. A lot of corrosion down there. We're looking at some stabilization, but that has to be replaced. So one of the things we're planning under this upgrade is a high-level pump station new up here in the top, that big blue box, and you see the green box. The main difference between those two is the flow we designed for. So the green box would be for 80 million gallon per day, and then the 160 the blue box is 110. So you see the footprint that goes up. We're trying to leave ourselves flexibility, and not us, but for generations to come, to be, once you invest and become compliant, you want to produce as much water as possible. As I mentioned in the beginning, very interconnected system, both through wholesale and retail plus emergency. So being able to produce flow when people need it, particularly at peak, that's something we're trying to incorporate into this upgrade to allow for the reliability and to produce more compliant water as needed for the region. So those are some of the design considerations. They're just the flow that we designed to. You see the high level pump station here. Oh, this is the clear well. Sorry, that we're looking at there in terms of the size of what we look at. New piping in the street. Right now all the piping comes out at the bottom and goes and shoots out into the distribution system. We're looking at, this is Riverview Drive. Large pipes to go there, one for Totowa, Verona, and Morris County, which is our wholesale system, and the other in the industrial and high service zones to the existing mains over there. So really, sending this flow where it needs to be, all new piping, and again, abandoning 120-year-old piping that, it's got to be planned for. So that's something we're incorporating in here. There is an interim pump station not shown on here because we haven't located it yet. But it's somewhere on site. There's going to be need to an initial pump station to take the flow from the filters, which are on the bottom right here, and move it. You can't see the topography, but this is uphill. It's pretty steep slope. So where we're putting the new It's gravity contactors, GAC, would be the post filtration PFAS treatment that we've selected. Would go right here. Sorry, my cursor's disappeared. Would go right here as a PFAS treatment facility. Well, maybe 16 units or something like that. So that's the conceptual footprint. Well, you got to pump it, because this is a much lower elevation where the current filters are. We have to pump it uphill to this treatment and then run it over here and to the pump station to pump it out into the system. So not a small site configuration. This is not just an add-on technology. This is a real reconfiguration of the site. Things we looked at, you see the Passaic River here all the way on the right. Well, can you cantilever? Can you go over the river? And add treatment down here and maybe avoid that interim pump station. And it wasn't feasible for a number of, there's wetlands, there's other considerations, there are environmental considerations, something we couldn't just do. And you see there's also a lot of existing pipes down here, very congested area, and that just wasn't feasible. So this was the best spot where we had land. Just there's always a price to pay, and one of the prices was interim pumping. So we needed an interim pump station that would be located somewhere down here, whether it's in one of the abandoned buildings down there, or we reconfigure some things and then pump it up the hill to this treatment facility, and then move it over to the clear well and out into the distribution system. So plenty to do there. Like I said, we just finalized our alternatives selection, like a short list. And what we're doing now is moving into conceptual design. They're going to take geological borings. There is a lot of shallow rock on this site, a lot of it. And we burned through two bobcats, and with the arms with the whole rams on them, just laying a 6-inch water main over the winter because we had a break on the site. It took 2 weeks just to go through the rock. So this is not an easy place to work. Topography-wise, as well as geology. We're going to do a lot of borings and also underground interferences. It's an old plant, as I mentioned, 100 years old. A lot of underground interferences that are not mapped. So we'd like, under this planning contract, go out and do test pits. Let's locate that stuff. Let's try to get the best sense as we can when we actually go in and reconfigure the site of what we're up against. Have a good cost, have a good contracting approach to do it as quickly as possible because of the timeframes. 2029. Oh, sorry. Go ahead.
I don't mean to interrupt you, but I just want to let you, we're past time, so we probably should, maybe move on to the wrap up. Thank you.
Yeah. So this is it. So we're going to finalize the conceptual designs by the end of this year. We'll include the geological borings that I mentioned. Identify appropriate phases, like what's the next phase? Is it a heavy site civil phase on the site and street work with new pipes? Maybe that can move in parallel. Identify appropriate project delivery mechanisms, whether it's design bid build or CMAR risk. Continuing to look at funding mechanisms. Like I said, 300 to 400 billion is the estimate. Not an easy elephant to swallow, right? You take it one bite at a time, but we're going to continue to look at that. And that's the overview of where we are.
Fantastic. Please add any questions in the chat. And we are pretty much at break. If you need the break, please feel free to do that. We're going to reconvene at 12:30, but we will take some questions since Jim is here, and we want to basically get your questions answered. So the first question is, why was GAC preferred over other emerging alternative adsorbents? What was the basis for the decision for the GAC?
Yeah, proven technology. Like I said, the timeline is 2029 as compliance, and I believe the federal have allowed another 2-year extension on that. I think you have to apply for it. It remains to be seen what New Jersey will do as the state, but it was a proven technology that we needed to get in design on. And that's why we selected the GAC. We're always trying to look. We're not shy to spend money on the piloting and time on it. But we can't also just keep pushing it off, saying something better will come along. We needed to make a selection. We've been at this for about 2 years and needed to advance. Advance forward. So that's what went into that.
Yep, that makes sense. Next question is: did you consider pack addition to the ActiFlow as a treatment option?
We did, and honestly, something as this gets closer, maybe even as an interim solution, it could be reconsidered. We did look at it. The couple downsides to it was, from a PFAS perspective, you still have to dispose of the residuals, and the anticipation is that will be tightened up over time as PFAS regs maybe enter the wastewater side of the house or residuals disposal, so that it would still be something that would need to be dealt with. We're not kind of getting rid of it. Same is true of GAC regeneration, by the way. So you're always dealing with something like that. The volume was pretty high as well, and the annual costs were fairly high for that. I believe the estimate was somewhere in the $10 to $20 million range for the size we are. Just for that. So maybe as an interim solution, it has a place. Say 3-4 years from now, if there's if the company's trying to come down on the compliance side, as a longer term solution, it didn't look like something that was viable.
And then I'm not sure if you mentioned it, but did you guys pick your design empty bed contact time for your basis of design? Did you select a number of minutes?
So right now, 20 is kind of the target, and from a footprint standpoint, we'd love to get that down to like maybe a 10 or a 7.5. But that's the additional piloting that DEP wants to see of like, hey, let's demonstrate that a bit, and we're still early enough. We have time, and so that's why it's a good iteration, even as we're finalizing conceptual designs. Shrinking that footprint would be great. Also, expanding the hydraulic throughput of the existing filters is in the plan. So a lot of good optimization here. The main risk, though, is that main pump station upgrade. That's really huge of just new pipes and new pumping. But good questions.
Yeah. Next question is, was there a second best safe choice after the GAC? Was there a close second? Like, who was in the running when you were making your final decision on the treatment? What were you comparing?
Yeah, I mean, we looked at Cornwall looked at pressure vessels, and Black & Veatch was helping us out with some of that. I'd say that there wasn't a great second. I mean, and we went here, we really beat it up internally. There was a lot of, good tension amongst the teams of trying to figure this out. Right. At the scale that we are, plus the time frame we're in, and the proven nature of what we needed to do, there wasn't really a great second choice. But again, lots of room for innovation as things evolve and maybe get more proven. You can always replace media. Once you put volume in place on treatment, you can always replace it with different things. So I think there's some flexibility going forward, but that's kind of where we ended up now.
No, that's great. And your final vessels, you're pumping, and you're going to be pumping to like concrete basins, or you're going to be pumping to steel pressure vessels?
It's gravity contactors.
Gravity contactors. Okay.
Yeah.
Makes sense for that side. Yeah.
Yeah. And then that's the goal by the end of the year, have the conceptual design plus the geological borings, get more real about costs, electrical load, right? What do we have to, some of the electrical systems out there are 80 years old, 60 years old. So there's a lot of ancillary things that have to come into place to make it all work. And that's really ahead. That's kind of the next 6 months of figuring that out.
Yep.
And then as technologies evolve or whatnot, you can always play around with those volumes and maybe put different media in or different things. So that's the trying to leave it as flexible as possible while trying to progress.
Was there any special attention to backwash equipment for, maybe if you have different future media, you may have different backwash requirements? Is there maybe
It's a great point. And it's a great point. And the backwash piece is a detail that still needs to be worked out in terms of trying to minimize that flow of what we have to deal with, and also make sure it's effective. So I think that's ahead of us to kind of really dive into that as part of the design in terms of how that'll work.
Great. Well, thanks everybody for participating in the morning session. Appreciate all the questions. And did want to thank again all our speakers, and especially now our final speaker, Jim Muller, being the executive director and fitting this into I'm sure, a very busy schedule. So Jim, we really appreciate some of your time and sharing with us all the good work you guys are doing with your partners. So thank you very much.
Thank you.
And we're going to take a break. We'll be back at 12:30 sharp, and look forward to this afternoon's presentations. And like I mentioned at the beginning, we have a 2 p.m. Recap of the day's, recap of what we learned, and a discussion and a chance for folks to ask other questions that they might have. So again, thanks, Jim, and thanks everybody, and we will we'll see you back at 12:30. The recording going? I always seem to forget that. Okay. Hopefully you can now see this. All right. So basically, 100 MGD water treatment plant. PFAS levels are hovering above the MCL. PFOA is the contaminant of concern, the one that's most often above the MCL. We do our water supply is the Wanakee Reservoir, and it's supplemented by the Pompton and Passaic rivers. So basically, that's where our problem comes in. You can see Pompton Passaic River levels are higher than our reservoir source, and the concentration of the raw water can vary based on the amount of pumping from the river and the reservoir level, as you might expect. So more pumping, more mass coming into the reservoir, lower levels, less dilution, and particularly in drought conditions, that can be more pronounced. One thing that's interesting, yes, sir.
Can you jump to the full presentation mode right now? You're in like a note view.
Okay. Yep. Let's see. How about now? Did that work?
Yes,
Looks
perfect.
good.
Okay, great. Okay, thanks. Sorry about that. Thanks for letting me know. So yeah, basically what I was going to say was, in 2024, they were entirely under the MCL. So wouldn't really need any treatment that year. But then in February 2025, there we are. We're above the MCL. So this next component is to talk about the idea that we developed together and what the promise or the hoped for promise of it would be. So we observed the work that was done by Orange County Water District, Megan Plumley and her team and her partners, including Scott Grieco, and we saw that they were getting really excellent PFAS performance, very high bed volumes to exhaustion. If you're not familiar with that media, it's a surface modified clay. It's characterized as a novel absorbent. One of the things that attracted us to that was that reportedly, unlike GAC, it's not impacted by TOC. We did learn that there is some TOC removal, but certainly not to the level that you see with GAC. And it was also reported to be able to permit chlorine residual, which was very important to the commission because their filters are part of their CT, and they also add chlorine to create a manganese dioxide coating on the media to remove manganese. So needed to be able to handle that. So the promise or the idea was basically, instead of building post-filter absorbers, put the fluorosorb media in existing filters and replace anthracite with fluorosorb. That's the idea. Kind of similar to what Scott talked about with GAC on top of fluorosorb. We just don't have any GAC. We're just straight fluorosorb, and off we go. So the promise or the hope was that we could save significant capital. I mean, this would be a total game changer. $500 million versus 25 million, and really simplified operations. And we got a flavor of what's involved when we heard Jim's talk, but no change in hydraulics here, no pump station needed, pretty much status quo in terms of the operation. These are some of the challenges and the questions, and there were a lot of questions that were asked. Can the media, step one, can the media perform as well as traditional filter media? Can it do as good a job as anthracite in things like turbidity, filter runtimes, backwashing, bed expansion? Can the media fit in the current filter box? We're going to have an issue with media expanding and then losing it in the backwash troughs. Can the media remove manganese? Will it allow a chlorine residual? I mentioned that because we need that for manganese and CT. What empty bed volumes can we achieve? What's the PFAS performance like? What's the water quality of the backwash water? Will the media hold up to abrasion and backwashing? Can we obtain a regulatory approval? So a lot of questions. that needed to be answered to be able to move forward with this. So what we did is we put together a testing plan. A lot of people are promoting site-specific testing, and that's what we did here. Basically, started out with a phase one, which is basically a pilot scale filter column, 6-inch diameter columns, where we just looked at filtration performance for different size fluorosorb medias. They're FS 200, 400, 600. We had an FS new. We had FS 300, which was anthracite and fluorocide mixed together. FS new they created just for us with a mesh size we thought was going to be effective. At the end of the day, we picked the FS 600. It did as well or better than the anthracite. We had anthracite as a control, so we could directly compare it to the anthracite sand. And we found that the fluorosorb 600 did as well or better than the anthracite for that phase. So we moved on to phase two, which was basically how does it do over a longer period of time, different water quality conditions, and how does it do for PFAS removal, which you can't really see in a short period of time, as everyone knows. We need time to see how long it's going to take. And then finally, I would say a very exciting component of the testing was testing at full scale. So after phase two, we decided as a team that the results were sufficient enough to warrant a full-scale test. So we put the media into their existing filter number 8. And the good thing was they were already in the middle of filter upgrades. They were getting new underdrains, new sand. They were going to replace the anthracite anyway. So the timing worked out almost perfectly, or really perfectly, to allow this to happen seamlessly with that construction project. So we put in, it just in terms of scale, it was 0.196 square feet, for the 6-inch diameter columns, and this was 2320 square feet. So a lot more media and getting to see like full scale, real world conditions. We ended up with 36 inches of fluorosorb, 12 inches of sand, and depending on the flow rate, 6 to 7.5 minutes of empty bed contact time. So just to share some of the results, and we do have a lot more than these to share. I will be putting something up on Figshare of all the results from the multiple reports that were prepared. But given our time limit here, I'm just going to give you the highlights. So this is filter performance. And if you remember, filter 8 was the one that had the basically had the best performance from a turbidity standpoint. Basically, it did better than the adjacent filters, which were more or less seeing similar water quality. So this was the turbidity, statistical average. Filter run times, also a good story for the fluorosorb media, had the highest, basic. Let's see this here, had the highest filter run times of any of the three media. So as a filter media, it was working, no issues with backwash, and performing well as a filter media. So in terms of the PFAS performance, this is where we hit some hurdles, some roadblocks, whatever you want to call it. The PFAS performance was not as good as some other alternatives, I will say. So when you look at this, it really comes down to the cost of effectiveness of the solution. And here we had a very low CapEx, but if you're replacing your media on a frequency like this, your operating costs start to go up, and it's no longer maybe the best option. And I will share with you the evaluation we did to compare that in a moment. But I'll share some of the specifics on bed volumes. This is not to get you too caught up on this, but this was trying to show, or it does show, this phenomenon of an early breakthrough that then settles out. So there's like an initial break-in period where the clay maybe has to expand or something, and then it kicks in. So these were some of our conclusions, or some of the answers that we developed. So for just about every question, the answer was yes. It worked really well as a filter media. Turbidity, runtimes, backwashing, bed expansion, all check the box. No problem with the media. and removed manganese swimmingly. We were able to maintain a chlorine residual through the filter, and that turned out to be very important because not having chlorine residual will affect PFAS performance. The bed volumes was where we kind of hit a bit of a challenge where the removals, 22,500 bed volumes for 30% removal, 17.5 at 50% removal, was leading to a change out frequency that wasn't going to be the winner. Basic bottom line. We did have data on the backwash water. I'm hoping Christina will be presenting that later this afternoon. And the media did hold up to abrasion and backwashing. And just to comment on Christiana's presentation, we did also see, the fines that she saw, and we did see elevated PFAS levels in the backwash water. So these are some of the insights, some of which I've already talked about, but basically the media worked well as a filter media. That was a big question we had. In fact, it performed better than anthracite. It's more expensive than anthracite, so it's not going to end up being your choice of media for non-PFAS applications. But in any event, it worked well as a filter media. I mentioned that break-in period where you think you've got no treatment, then all of a sudden you do have treatment. We did find that we needed chlorine residual to prevent biogrowth. During phase 2A of the testing, we had abysmal results. We realized that our chlorine levels that were coming in from our settled water were not what we thought, and we were getting abysmal performance. We realized that adding chlorine was super critical. We added chlorine to the full scale as a sort of to augment what they already had. This is more of a theory than actual proof, but we basically believe that the biogrowth, manganese armoring, aluminum armoring from the flock particles, some TOC removal are all conspiring to reduce the PFAS removal effectiveness. We're just asking this media to do a lot. It's got a lot to deal with, and that's affecting the performance. We did see higher empty bed contact time. We got better results. Like I mentioned, the PFAS in the backwash water, we did see that. So there would need to be something there, either a filtration step or a way to remove those particles. We did see that DBP levels increased in the water, not to levels that were problematic for this utility, but because of the addition of chlorine, we did see DBP levels increase. So if there's one sort of hope that I have in all of this work, is that this last idea might work for somebody. And this is our sandwich media configuration, which is basically looking at taking light anthracite, which has a density a little bit lighter than the fluorosorb, putting that on top, say 8 to 12 inches, then your fluorosorb, then your sand, and letting that light anthracite be your sacrificial layer, take up some of that manganese, take up some of that aluminum, free up your fluorosorb just for PFAS. Unfortunately, when we did our testing, we got a little too aggressive on the manganese, and we overloaded this particular configuration with way too much manganese that they would ever really see, and so our PFAS performance was not great. So I'm going to move on in the interest of time, and I only got a few minutes here. But basically, we in parallel with the pilot testing, we did an engineering evaluation with HDR. Very pleased with that work. This is our planetary chart with comparing different alternatives. On the left side, you have net present value, and on the y-axis, on the x-axis, you have performance score. So where you want to be is in the lower right-hand quadrant. And so you see here that PAC, powder activated carbon, was the winner, but not too far behind was the Setco. But just comparing everything, led us to consider moving towards PAC. So that's what we did. Pivoted to PAC. I'm going to share quickly some results here. Looked at 18 different PAC products. Again, want to acknowledge the work here of Ethan Snyder, Liliana Cordoba, Maureen Nesser, and the whole lab. This is all work they're doing in-house, and we're really happy to see good results with the Ingevity AquaNuchar product for this water, levels that are good percent removals. We did additional testing on our top products, the AquaNuchar, the Arc Carb, and the Calgon product, and the HydroDarko. And the good news for the commission is that somewhere between 10 and 15 parts, they can achieve the target percent removal that they're looking for. I should mention that they like this option in particular because you have the ability to turn it on and off. And if you have levels that are below, then it's off. And if the levels are above, then it's on. And that's attractive to the commission. It also did really well with geosmin, the one product, the AquaNuchar. So instead of having potentially multiple packs, they may be able to just go with one. We also did a USGS characterization study of PFAS in the watershed to see if we could find some hot spots and track back where the source is, because we're just above the limit. And we have multiple water suppliers in this watershed, including American Water, including Passaic Valley Water, Veolia, the Commission. So we thought it'd be worthwhile to investigate what's going on in the watershed. 37 sites, 4 different sample periods for base flow, some wet weather events, and generated a lot of good data, and now have it all available in an interactive dashboard that anybody can access. It's available to the public. We did find one hotspot, so that was worthwhile, and we're continuing to do additional work. But we did also conclude that this is widely diffuse. It's in domestic wastewater, and we're hoping we can still find some other hotspots, but it's a widespread diffuse problem that's everywhere all at once. They did upgrade their analytical. They now have their own waters testing equipment, so that's helping them with all this work. So in summary, a lot of good work was done. Some innovative testing on the novel absorbent. We think there's some hope with that sandwich media. Great cooperation from EPA on the backwash water, foam, and residuals testing. Great collaboration with USGS on source water sampling. Fantastic work by the lab staff on doing all this testing work with their new equipment, which they installed themselves. Great support from DEP, Corey Stevenson, Joe McNally, and the team there at DEP supporting us during all this work. The feasibility study, comparing alternatives. Doing the jar testing. We're planning on doing full-scale testing in the summer with the AquaNuchar. This webinar, and then they're planning on moving forward with likely pack design and construction. So I know I'm just about pretty much at time, but I do want to share this idea, which is basically the creation of a healthcare support fund from the percent of earnings on PFAS-related work. And the idea would be that the fund would help families defray costs of medical care for their children facing adverse health effects from exposure to elevated PFAS. And the idea would be suppliers, vendors, utilities, consultants, attorneys give a chance to give back what they've been receiving for all the work they're doing. So it's in the initial exploratory stages. If you have any interest in that, please get in touch with me. And then finally, I want to thank the full team for really a terrific collaborative effort. I'm not going to name everybody, but I am going to name the commission team. So Sally Avalenda, Tim Eustace, Paul Cirillo, Keith Smith, Jose Pita, Maureen Nesser, Paul Carney, Ethan Snyder, Jason Borner, Maria Allegro, Liliana Cordova, and Liam O'Reilly, and a host of others that were really instrumental in doing all this work. Great partnership with all of these firms, and really appreciated the collaborative effort. So with that, I will see where we are time-wise and see if we have any questions. So thank you very much. I'm going to stop sharing. I'll let Joe go ahead and share. I'll see if we have any questions here. Get rid of this. Get rid of this. Look at the chat. Okay, so we got some questions here. Any concerns about backwashes taking fluorosaur media with it? If so, where can you discharge, sewer or ground? Great question. Yeah, we are concerned about that. They do have a backwash holding tank where we expect that to settle out. But you do have the issue of like recycling, fluorosorbent. At some point, you need to get that out. And so there might be a need for like a cartridge filter or something on the backwash water. And then in terms of their ultimate backwash water, they have ability to dewater, thickening, and belt press. And then they go to their lagoon and they're monitoring that. And then, yeah, so that's all basically something that they're looking at very closely. So yeah, discharge currently is ultimately goes back to the reservoir, and they do recycle a portion of the backwash water back to the head of the plant. What was the approximate break-in period observed for PFAS absorption? Very short. I think it was in the order of, in terms of the testing, maybe a week and a half for the full scale. So a very short period of time. Next question. Was the initial media and spent Setco media analyzed for manganese to see if there was an increased level? That's a really good question. And the answer is yes. We did have Bill Nocky analyze the media. We crushed it. Can't recollect at the moment the results, but it definitely was, the media was removing manganese. We saw it in those samples, and we also saw it in the reduction of manganese. What were the TOC levels in your water, and also what DBPs did you measure that increased? So I'd love to have Maureen Nesser come off here, but I will try to answer this. So TOC levels are really low for this utility with the reservoir. I think it's usually sub 2. And DBP levels were HAAs and THMs, and those increased slightly, but not to the level that it was of concern. Last question, could a multivariate approach of Setco and the filters and PAC be considered? Yes. Yep, absolutely. That could be considered. It becomes a question of, I would say the cost effectiveness of that. And if we could achieve it with one and not the other, that might save some cost, but certainly PAC with Setco. And we do have some data on that because we were adding PAC for other reasons during this work. And so we were getting kind of a 1-2 punch with PAC and then the Setco. So, all right. Well, thanks for listening to my presentation. We're going to shift gears now and welcome Joe McNally from DEP. And Joe, just do me a favor, hit the hide button on that annoying Zoom. There we go. And
Sure.
You can take it away.
Okay, great. Everyone can hear me okay?
Yep, good.
Great, perfect. All right, thanks, AJ. So good afternoon, everybody. My name is Joe McNally. I'm an environmental engineer with New Jersey DEP's Bureau of Water System Engineering. My focus is in our surface water treatment unit. We regulate the surface water systems in the state. And PFAS lately has been a big focus of our work as systems have been coming in for construction permits, submitting PFAS pilot reports, requesting input support from DEP. So it's been a big undertaking. This webinar has been pretty good so far. It's been great, a lot of new stuff. Also seeing a lot of familiar things as well with what we're seeing in New Jersey. So we might not all necessarily be in the same exact boat, but we're all floating around in the same sea, for lack of a better word. So that's some background. New Jersey DEP, we adopted MCLs for PFNA and PFOA back in 2018 and 2020. Also PFOS. Down at the bottom there are those limits that we set. So through 2025, we had approximately 44 community water systems have PFAS above New Jersey limits and received MCL violations. All of those violations were for systems with a groundwater source, so they're all groundwater systems. We did have a surface water system and a GUDI system with PFAS levels in their source above New Jersey's levels, but they were proactive and installed treatment before they could receive an MCL violation from New Jersey. Also, a thing of note is we're going to be using PQL of 2 parts per trillion compared to 4. So anything above 2 or below 2, I'm sorry, will be considered non-detect compared to 4. So that will affect, the system's approach to their PFAS treatment designs. So for some perspective, New Jersey, we have a total of 28 surface water systems, an additional 7 separate GUDI systems. Of those 28 surface water systems, about 20 of them will need to install treatment based on their source levels of PFAS. 3 of them are small, less than 10,000 population. 4 of those 20 are medium, between 10 and 50,000 populations. And 13 of them are large systems, over 50,000, with about 8 of them with populations over 200. So in short, the systems that are going to need treatment are big, not many small systems. For like a kind of idea of what the plant capacities are, most of these surface water systems only have 1 treatment plant. A couple of the bigger ones have 2, one even has 3. But, there's a range of 30 MGD all the way up to 100 MGD. So when it comes to the road to compliance for PFAS, installing treatment at the plant obviously isn't the only hurdle systems are going to face. So for example, the systems has to consider, PFAS in the backwash water and the residuals. That'll have to be planned for depending on the treatment approach. There's also going to be various permits required for the large scale construction that's going to be involved with these facilities. A lot of these bigger systems, you're looking at massive warehouses with vessels, contactors that might even double their, treatment plant existing footprint. So things like considerations for wetland protections, flood hazard areas, and stormwater runoff. So to help these systems with meeting the 2029 deadline, New Jersey DEP, we created the PFAS Permitting Solutions Team. So what it is an initiative intended to provide permitting and regulatory assistance to potable water systems that are planning to install PFAS treatment. The goal is to ensure that these projects are not delayed or held up by long permitting times or outstanding issues. This is achieved by direct communication between the permitting solutions team and the potable water systems. Typically, an initial meeting is held with the facility where the project is presented to DEP staff, who then provide input and comments on applicable permits, approvals, any specific regulations, or identify potential issues with project planning. So this is relatively new. We've met with a few systems so far, and we plan to do so with the remainder in the future. This is just a list of every program included in the team. It goes from land use and watershed protection to our water quality, wastewater group, air quality, flood engineering, waste management, flood engineering, green acres, a whole bunch of different groups. So, and this stuff includes wetland letter of interpretations and the GIPD's permits for discharge, treatment work approval, solid waste permits, flood hazard area verification, and so many other that you can see, on this slide right here. So if there is any possibility the public water system will need a permit from one of these groups related to their PFAS treatment construction, we include them to move in the meetings to move things along as fast as possible. So this slide summarizes what we have seen and experienced in New Jersey so far with PFAS treatment. As of today, we've approved one construction permit for PFAS treatment with another in-house. The approved permit was for GAC vessels and lead lag at about a 25 NGD plant. The other permit we have in-house is for GAC contactors, not in lead lag, for a plant capacity of 60 MGD max. 8 other systems have ongoing or completed piloting to evaluate PFAS treatment options. Several systems have gone through multiple phases of piloting that have been, taken 2 to 3 years to complete. Some systems are just getting started. A handful of systems that are doing the piloting come in for a temporary treatment approval as well. That's a situation if the treated water going through, for example, the column testing goes into the distribution system, we'll need a temporary treatment approval. But if it's all just going to waste, it's not necessarily a type of permit we would need. So in short, a lot of systems are working hard to figure it out. So some of our friends in the regulated community already presented today from a few different systems, but based off what we've seen so far, each system has unique challenges and varying water quality that warrants piloting to come up with a solution to the problem. So what we're working on is developing internal policy that will require all surface water and GUDI systems with PFAS above the MCL to conduct piloting.
Hi, Joe.
Yes?
Hello.
Does someone
Yeah.
have a question?
Hi, Joe. How are you doing?
Hi.
I'm doing good too. What can I help you with?
Yeah, we're in the middle of a presentation. Maybe you guys can catch up later.
Oh,
Go ahead.
okay.
Go.
Yeah, I will let Olivia or Jackie know. I will let them know, and they will contact you. Is that okay?
Yeah, thank you. So where did I leave off? I apologize. So we're working on internal policy requiring systems to do PFAS pilot studying. So there's various piloting approaches that we're considering acceptable, whether it be bench testing all the way up to full scale. Once the pilot is finished, a report with the results and all required data must be submitted to our Bureau of Water System Engineering for review. If the treatment proposed is something conventional, just your lead lag, JSE contactors, or ion exchange, the pilot report can accompany the construction permit when that's submitted to the Bureau of Water System Engineering. If the treatment is a more unique approach, for example, replacing filter beds with a different type of media, having empty bed contact times much lower than 20 minutes, then the pilot should be submitted to us for review and approval so we can provide input prior to the system submitting that construction permit. So some details of what must the pilot study include. For column testing, which is what most systems have been doing so far, these include information like the total number of columns per skid, the different types of media that are being tested and their configurations, media depth, number of sample ports, etc. We're also asking for a monitoring plan with all the parameters to be sampled for, their locations and frequencies. For example, things like pH, iron, manganese, turbidity, TOC, chloride, obviously PFAS. So everything that's going to be relevant based on the system's water quality, we would like to see, what your plan is going to be for that. The pilot also have to acquire enough data for empty bed contact time, surface loading rates, bed volumes to break through and expected media life, PFAS levels, and the influent and effluent of the pilot study, all key information that kind of help support potential treatment designs in the future. Testing will also have to be done under the various flow rates a plant can experience to demonstrate PFAS removal is effective at all times. At least evaluating flows, based on plant's average day demand all the way up to max day demand. Lastly, we strongly recommend systems complete piloting for a full year to evaluate treatment effectiveness under various seasonal conditions. The water quality coming in the winter compared to the spring can definitely affect your PFAS removal depending on the type of media and what treatment approach you're looking at. So here's a few specific situations that have been evaluated by systems. Some systems have been looking at much lower empty bed contact times in the 5 to 10 minute range based off of support or variable research that's out there. Some of these systems, the piloting data looked favorable, but we went back to them and requested some additional testing to be conducted in their pilot to support it. Several systems have investigated replacing their filter bed media with a finer GAC or a novel media to balance filtration and absorption. It's an option that obviously save a ton of space, so that's probably appealing to systems, but the feasibility does seem to depend on the source water levels of PFAS present and then what the cost would be for media changeouts. If a system is testing out different media in their filters, we do require particular data be collected to ensure simultaneous compliance as well. This includes continuous turbidity monitoring, TOC sampling, evaluating head loss, maybe even looking at DBPs, as well. We also require systems to collect this data from other filters that are not testing out the piloting data. For example, whatever original media you have in there, as kind of like a comparative analysis to make sure that, there aren't too significant differences between the media. For example, if you're getting like an average of 0.3 NTU coming out of your piloting media, but the rest of them are doing like a 0.1 average, might be something you need to take into consideration to make sure the simultaneous compliance. Biologically activated carbon pre-ion exchange has also been looked at. It seems like surface water systems, UDI systems, are experiencing fouling pretty often with the ion exchange, and a solution for that is, BAC, which seems to help when it comes to allowing the ion exchange to focus on PFAS removal. We've also got systems, looking into jar testing, considering PAC as a treatment solution for PFAS. Okay, so a couple more slides. So with the challenges surface water systems are facing in approaching PFAS treatment, we are open to design considerations that will vary from the regulations. However, the system is going to have to justify it. So vessels or contactors not in lead-like configuration or achieve less than 20 minutes of empty bed contact time as common options systems are evaluating. For large systems, it may not be feasible to construct vessels in lead-like configuration due to the cost, space constraints. As discussed earlier, systems will still have to support this through piloting data. We'll also need about how they're going to evaluate media performance and prevent PFAS breakthrough if they're not in a lead-like configuration. The piloting results should kind of give the systems an idea of their media life, but enhanced monitoring is something we're considering in water system engineering as a construction permit condition, at least in like the beginning, to make sure that PFAS removal is working effectively. Also, like the redundancy, figuring out what's the right amount of vessels I have as a backup, depending on the range of flow systems can experience throughout the year. Is it N+1, N+2, 3, or 4? It depends on the system design, but they will have to support that number as well. We're also going to be asking for an operations plan. Obviously, with all of this media, a single vessel could hold, several hundred cubic yards of media. That could be a lot of media coming on site, off site. So this operations plan will kind of include, how systems are going to, prevent and manage breakthrough, what the change out frequencies are going to be, how much media is coming on site, off site, what the delivery logistics are going to be, if a shipment's delayed, how it's going to be handled, stuff like that. There's also been talks about blending. We don't really like that word here at New Jersey. DEP, but under certain challenges with PFAS, it's something that we're listening to. It's something that would probably only be approved for a small percentage of flows above peak daily demand. If it is something that would be approved, there would be conditions from the system. For example, developing a watershed management plan, trying to reduce overall PFAS levels in the watershed if possible. Finished storage maintenance plans, keeping storage filled as much as possible, especially during those peak flow periods. So there's less water being diverted and being blended with the treated water. Enhanced monitoring that would be used for like running annual average calculations for compliance. Then an operations plan, like mentioned previously. So next steps for New Jersey DEP, more construction permits are expected by end of the year. We've got several active pilot studies and temporary treatment approvals. Our plan is to formalize our PFAS policies for piloting and treatment and to communicate that with our surface water and GUDI systems. We also want to continue developing our design consideration requirements. We're going to continue to work with our PFAS permitting solutions team. And lastly, you're going to be follow up with the systems that need treatment to offer support if we haven't heard anything from them yet. And that's it. So appreciate everyone's time.
Yeah, Joe, thank you very much for presenting. Really good to get the perspective of state regulator in the midst of a lot of work going on. So thank you very much.
Absolutely.
There aren't any questions. I know Nadu, you came off mute there at one point. Do you have a question that you can put in the chat? If so, please put it in there. Asking all questions to be in the chat. So we do have one question. When can we expect a new policy to be published?
So it's something that we have drafted and we have it sent to like our management for review. So it's hopefully something, that we work to finalize in the next couple months.
All right, couple months. Thanks for the question. All right, let's see. Okay, good. All right, Naidu, you're good. Yeah, I apologize for cutting you off there, Naidu. I just that was a unusual interruption, but I apologize for cutting you off. I'm glad we're all good. So Joe, thank you very much. We're gonna shift gears now and ask Jackie to share her slides, and we'll get going. So Jackie Logston is with Kentucky Energy and Environment Cabinet. Welcome, Jackie. Thanks for being here.
Yeah, thanks. Do you see my slides and can you hear me okay?
Yes, perfect.
Okay. All right, awesome. So hang on just a second. This popped up on my secondary screen. So I was trying to get the settings just right. Okay. So anyway, I'm Jackie Logston and I'm with Kentucky's drinking water program. And I have been heavily involved in the implementation of the PFAS rule. And so whenever I was contacted about, hang on just a second, I'm having trouble getting my slides to advance. There we go. I was asked to talk about what systems in Kentucky are doing to address PFAS, but also to include a little bit about what we're doing on the state level. So I'm just going to go through quickly and briefly what we're doing on a state level here in Kentucky to track systems and support systems. And then I'll jump into what our systems are doing. And then at the end, I'll focus in on one system. So here in Kentucky, we started monitoring for PFAS back in 2019. That was a pretty proactive approach that our agency took. And it was just to gauge what was going on out there. And there was just a sample of systems that were selected. I think we sampled about 81 community water systems back in 2019. Then in 2023, when we were hearing about possible rules coming out, we decided to go ahead and sample the rest of our community water systems. And with the sampling efforts in 2019 and 2023, and then with some early results from UCMR 5, we had a complete picture of, well, not a complete picture, but we had at least one sample set from each producing community water system in Kentucky. We were able to take that information, do some additional sampling to expand on the systems where we had some higher results. At this point, we did have some proposed MCLs. Those were the ones that we looked at, any of those that had anything above a proposed MCL to do additional sampling. From that, we identified 17 systems in Kentucky that had at least one result above a proposed MCL. That includes surface water and groundwater, but the majority is surface water. The majority of systems in Kentucky are served by surface water. And so we use that data to determine who we thought might have a problem and who needed some assistance. And if anybody's interested in our data, it's all available there at that QR code. So what we started doing immediately was offering system-specific support. We made site visits to all of these systems just to have a sit-down conversation about what it meant and what they needed to be thinking about. That support continues today. We're still sampling at water systems. We haven't stopped since 2023. We've continued to sample, and we are working one-on-one with small systems and a few of our large systems, but most of our large systems are working independently, but they're keeping us informed on what's going on along the way. So some of that sampling, we've done sampling support. We've provided guidance on evaluating treatment options. We haven't done a lot of the evaluating ourselves, but just providing guidance on how they can approach that. And then working with systems to provide funding through the ECSDC grant. One project that we took on in our agency with our technical assistance section was a jar testing project looking at powdered activated carbon. And we've heard some talk about that already the last couple of days, which has been really interesting to me to hear about, because whenever we first started doing this, it was kind of a new thing for us to be looking at. We were inspired by the work being done at Louisville Water, and that's the system I'm going to focus on when I get further on in the presentation. But the reason we started looking at powdered activated carbon is because we have a lot of small systems. When I say a lot, out of the 17, a lot of those 17 systems are small systems, and they have PFAS levels that are slightly above the MCL, and maybe even have results that aren't always above the MCL. So there's a potential for compliance issue, but maybe not. And it's really hard to justify the amount of money that's going to be required to install the infrastructure needed to treat PFAS if there could potentially be a less expensive option. In Kentucky, we require surface water systems to already have the ability to feed powdered activated carbon. So we thought that was a good place to start. The treatment considerations that we were looking at were the types of PFAS that needed to be removed. What are the treatment goals? Is the goal just to be in compliance? Is the goal to be below the trigger level, to be on reduced monitoring? And then really looking at the site conditions, looking at the raw water quality, what other competing factors would there be for the powdered activated carbon like TOC, and also looking at the plant design. With smaller systems, they're likely to have less contact time, less settling time, potentially filter issues with the pack. So we knew that there would be some limitations on how much they could feed. But really our project goals were to screen for treatment efficacy for specific systems and inform in-plant trials. We don't have a large capacity in providing a lot of one-on-one technical assistance for this project, but we felt like we had enough that we could do some of that pre-screening for them and provide the information that they could then dig into a little bit deeper with their engineer or consultant. Now looking at what some of our systems are doing here in Kentucky to address PFAS. We do have one system that has already completed a project. They were identified early on in 2019 with some really high levels of PFAS. And so we were able to get them funding through the ECSDC during that first round of funding. And they have already secured a new purchase source that was able to eliminate a treatment plant that had contaminated groundwater wells. So that one is complete. But under our ongoing projects, GAC is the most popular option in Kentucky that water systems, that surface water treatment systems are looking at, because it has that added benefit of the DBP formation potential being lower. With the GAC. We have, like I said earlier, we have a high percentage of systems that utilize surface water as a source, and we have a lot of consecutive systems in Kentucky, and most of those consecutive systems are purchasing surface water, so we have high water age as well. So we've got one that's already approved, 4 that are in the design phase, and 2 more we're expecting soon. And then under powdered activated carbon, we have 2 systems that are already effectively utilizing PAs, using the pack. And then we have 3 other systems that are evaluating it as a potential option. And 2 of those are ones that we conducted the preliminary jar testing for, and they decided to move forward and dig in a little bit deeper with that option. We also have a system that has already been approved to build a reverse osmosis treatment plant. And then we have another one evaluating moving their intake to a new source, and then another regionalization effort going on to eliminate a small plant. And now I'm going to jump into the work that's being done at Louisville Water. And just, I have not been directly involved in the work at Louisville Water. However, they've been very open about the work they've been doing. They've shared with us many times what they've been doing, keeping us updated on the progress throughout time. And I find it interesting, again, going back to the systems that have PFAS that are just slightly above that MCL, that you need to do something. But again, the cost of installing such expensive infrastructure for the moderate removal that's needed. It really forces you to think outside the box before you make such a large purchase like that. Louisville Water has 2 water treatment plants. Crescent Hill is the one that I'm going to be focusing on. That's a 180 MGD plant. They treat water from the Ohio River. PFOA is the only PFAS compound that has been consistently detected above the MCL. It's not always above the MCL. In fact, their running annual average for last year was a 1.9. But again, they do periodically see results about individual results above a 4. And without some treatment in place, this could be a potential compliance issue. So the reason that they decided to evaluate the powdered activated carbon, it was already a well-established treatment approach for source water events, organics and spills and that sort of thing. And again, only needing to have moderate removal of PFAS was a big driver in this because powdered activated carbon has been shown to be effective for moderate removal of the long chain PFAS. It's flexible and adaptable and can be adjusted based on source water conditions. They knew that this would have minimal impact on their treatment process already in place because they already have a PAC treatment system, and then it reduced that infrastructure cost need. Looking at the study that they conducted, so they've done extensive jar testing to study the treatability of the powdered activated carbon. The 2 that performed the best were there was one that was a wood-based PAC and the other was a wood coal blended PAC. The wood-based achieved anywhere from 15 to 90% removal across the dose range of 25 to 300 pounds per million gallons, which is about a 3 to 36 part per million feed. They are a lime softening plant. So that was also a consideration for them, just because coagulation and lime softening can interfere with the PAC performance. And so that was something that they had to keep in mind as they were moving through this project. And then again, considerations that they were looking at were competing organics that can affect the effectiveness of the PAC for PFAS removal, but also the benefit of decreasing that DBP formation potential by the removal of those DBP precursors. And so here is a graph that's showing 7 different PACs that they tested over a feed rate of 25 to 300 pounds per million gallons. And you can see, I don't have the name of each particular PAC, but the PAC 6 is that purple line that seemed to have the most impact. Again, this is looking at the removal of the PFOA. And then here's a graph comparing the jar testing to the full-scale trial that they did in the plant. And those lined up pretty well whenever they did the full-scale trial. So Louisville Water, after all of this time spent researching and testing, they decided that powder activated carbon was the best practical option to meet the regulatory requirements. They're able to achieve their goal of getting all of the results below a 4 part per trillion. They estimate an infrastructure savings of around $300 million. They're able to maintain their operational flexibility and familiarity. And then again, the additional benefits of the reduction of pesticides, herbicides, DBPs, taste and odor, and all of that you typically get with surface water. Future work They are, even though they already have a pack system in place that is working, they are upgrading that pack system so that they can have more storage on site. They are developing and optimizing their PFAS monitoring and treatment protocols. A big project that they have going on right now is evaluating their waste residuals, and then continued investing long-term advanced treatment technologies in their treatment process. And I did include their contact information here for anybody that is interested in more information. They've been really helpful to us on the state level as we're looking at smaller systems. And I know that there have been a lot of systems outside of Kentucky that have reached out to them for additional information. So I know that they would be more than willing to talk to anybody that has additional questions.
Fantastic. Jackie, thank you so much. Really appreciate your presentation today and your perspective. And I will just second the support that Louisville Water has provided. They've helped the commission out. I visited the plant you mentioned, and super helpful work that they're doing. We do have a couple questions here from our participants. Do you know, for the plant that's using RO, do you know what their plan is for the RO concentrate?
Well, in their engineering design, they had a spot listed for future treatment, and it's just kind of open. There's nothing been decided, and they said that when effluent limits are established, then they will address it at that time, but they've just noted that they're aware that that is something they will have to do in the future.
Okay, and then the next question is related to their disposal of the pack residuals. Do you know anything about what, for I guess Louisville we're talking about, what they're doing with the residuals?
I'm not real familiar with what they're planning to do. I know that Louisville Water has a very large capacity for waste residual disposal. I know their lagoons are really large and can go several years without needing to remove any sludge. Right now, the majority of, I say the majority, but the systems that are currently handling waste residuals, any of them that were doing any kind of land application have pretty much stopped doing that. Not because we have any regulatory language for it, but just as a recommendation and a good steward, I guess. And most of them are landfilling.
Yeah, and that's a good point. The way they feed the pack, they've got these massive lagoons, so they're not, for example, like at Awassa, where it became part of their residual stream and had to be disposed of with the residuals, whereas Louisville has these lagoons up front and they can go, eventually they have to get it out, but not the kind of frequency.
Yes,
yeah,
that's right. Yeah.
Well, again, Jackie, thanks for joining us. Really glad to have a perspective of a state regulator, and thanks for all your help to the commission as well.
Yeah, thank you.
So I'd like to welcome, this is speaker number 16. This is our final presentation of the webinar. Really happy to welcome Christina Costello from US EPA this afternoon. And Christina, you can start whenever you like.
Okay, thank you so much for having me. So today I'm going to talk about the RECESS research initiative. It stands for Removing Emerging Contaminants Through Engineering and Science Solutions. This initiative began in the Office of Research and Development, but it has since transitioned to the Office of Groundwater and Drinking Water. But I want to make sure that it's noted that we still have collaborators in other areas of the agency as well. This is just a standard EPA disclaimer that the views expressed in this presentation are those of the author and that we do not endorse anything that we discuss. So first, I'm going to share a little bit of background about the RECESS Research Initiative. which includes like the project team overview, as well as some information about the initiative and a map of sites where we have ongoing research. And then we're going to get into the meat of the presentation with research results from several case studies on PFAS in foams and source water and within treatment plants, as well as PFAS released during the backwashing of filter media, which you foreshadowed wonderfully, and the PFAS treatment pilot that we have at one of our surface water plants. And then we'll go into some general takeaways and we can have some questions. I want to note that the recess team is composed of principal investigators, which lead the individual research efforts, of which there are several, subject matter experts and support scientists that contribute to the research, as well as contractors, which are supporting some of the ongoing site monitoring and in-house analytics, as well as internal collaborators, like some of our other technical assistance initiatives, and external collaborators, including federal and state agencies, of which several are listening in on this talk right now. Thank you so much for joining. So there are 3 core components to the Recess initiative. The first one is treatment evaluation and optimization for bench, pilot, and full-scale systems. I'm going to cover this when we're discussing the piloting case study in more detail. We also have applied research that can be used to answer unique treatment questions at individual facilities and fill some knowledge gaps that we've identified. The foam and the backwashing research falls into this category. And then we have knowledge sharing and guidance development, which is informed by our technical assistance and research efforts. And that facilitates nationwide access to much needed information. And we can also use the data generated to enhance our agency models, which we will discuss later, but that falls generally into this category. So this is our map of sites. We have a total of 37 partner public water systems in 8 out of 10 EPA regions and 17 of 50 states. We have on the map recess supplied pilots depicted by pink triangles separate from our other sites, because we're going to be discussing those as well later in the presentation. And then the proportion of these sites that are full-scale treatment versus pilot treatment is shown in the pie chart. And the scale of the full-scale systems is shown in the graphic below that, where you can see some of our much smaller systems across to our largest systems. Right now we have 17 sites that have ongoing long-term monitoring, and of those, about 60% of them are treatment pilots, and 2/3 of them are public water systems serving less than 10,000 people. And we have 5 sites where monitoring is completed, and we're going to begin closeouts. So first, I'm going to be discussing surface water foams, as the research that we've done on surface water foams has influenced various aspects of the research discussed in this presentation. So it's known that PFAS accumulate at the air-water interface and that some PFAS are enriched in foam according to their chemical properties, like longer chain PFAS have higher enrichment factors. In general, the foaming potential of surface water is predominantly dependent on water quality characteristics like the amount of organic matter, weather conditions, and if there's presence of an aeration mechanism, like a waterfall or a dam, as you can see depicted here. You've got a little bit of both going on. And then we're looking into if in-stream removal of foam has the potential to be like a novel remediation technique for low flow stream where foam is generated in large quantities, potentially like what you're seeing here, either naturally or intentionally. So the pictures on this slide show examples of the range of foams that we found in surface water. Our team has been working on gathering sampling and analysis approaches for PFAS in foam, which generally include having field replicates and possibly compositing foam, similarly to how it's been done previously for soil and sediment. We've also found that PFAS direct injection method using SW846 method 8327 or an equivalent type of method works fairly well. And then getting moisture content similarly as to how you would do that for like a biosolids or residuals analysis. And we've been evaluating how to report PFAS concentrations, whether they should be reported as aqueous concentrations in nanograms per liter or dry weight in nanograms per gram, depending on the moisture content. In many instances, we have found that foams contain specific PFAS that are not detectable in subsurface water, but they are enriched in the foam to detectable concentrations. So we will also be discussing this later in the drinking water foams. On this slide, you can see the data in the table is listed for PFOA and PFOS in surface water for 4 sites. PFOS has a higher enrichment factor at all of the sites. So for each column, the water is going to be on the left, the water concentration, and the foam concentrations on the right side. In this case, the reference site is in Minnesota. It's that first line. So this is an example of a location where we've had low PFAS concentrations. In the past, the concentrations we've reported there for water may not have even been above the detection limits, but they were still found at high concentrations in the foam, which would have been able to be detected. So note that there is a difference in the concentration and enrichment between like the Minnesota sites there, where the contaminated site has PFOS enriched by 100,000 times, while PFOA is enriched by 500 times. In contrast, the reference site, PFOS is enriched by 700 times and PFOA by about 100 times. So that's just some of our interesting data. And then for AJ, you can also see the New Jersey site replicates that we have reported there as well. Yeah, but generally speaking, we're finding PFAS at high concentrations in these surface water foams. And this New Jersey site in particular is an area where they do a lot of recreation and fishing. So seeing these high concentrations in a lot of foam was a concern. So now we're going to talk about drinking water foams. So we started investigating these drinking water foams after noticing their presence throughout treatment at some of our partner utilities. This basically was happening at the same time as we were starting our surface water foam work. So we visited several utilities where we noticed foam was building up at different points throughout the treatment process. You can see this collage that I've put on the slide, where you have 3 separate public water systems. In this case, one is in Ohio, one in Kentucky, and one in Tennessee, where you had foam occurring during processes like aeration, after weirs, and also in areas where the addition of a treatment chemical has occurred, such as like alum or other polymers. And so this led us to have several questions. We're interested in knowing if the foam that was generated during treatment also contained PFAS. And if they contained PFAS, what were the implications for the utilities management practices as well as operator safety, as many utilities are spraying down their foams, and so they have concerns about that. Are the high concentration foams impacting PFAS monitoring potentially? Is there a treatment approach that we could leverage based on foam formation potentially? And so some of our research questions that we investigated or are currently investigating include evaluating how the foams build up and if there is an equilibrium that is reached. We investigated this by determining the amount of time needed for foam to build up. Again, once we removed it, we hope to further elucidate the characteristics of source water and the treatment conditions that might contribute to this foam formation. We also aim to characterize the high solids foams or float and determine the role of the enrichment and whether it's based solely on absorptive processes or if it's truly enrichment, which is driving the different PFAS profiles. You can see there on the left what I'm talking about when I'm talking about the high solids foams. So these are not uncommon. We also want to determine if the removal of the foam can be utilized as an alternative or supplemental treatment approach to lower the PFAS concentrations in the water enough, either to impact compliance or, which seems more likely, perhaps to extend the life of expensive sorbent medias. And we wanted to understand if the presence of PFAS-containing foam is an indication that foam fractionation might be a reasonable treatment approach. So to answer these questions, we conducted field reconnaissance to identify locations where foam was naturally occurring throughout treatment. And we also evaluated approaches for sampling the foams at the drinking water utilities. We ended up using often a nylon pool net to scoop the foam up. We also chose to composite the heterogeneous or high solids foams, generally in a stainless steel bowl where we mixed vigorously before portioning them into pre-weighed centrifuge tubes on site, which allowed for easy transport and then whole sample extractions in the lab. So you can see us going through this process in the pictures on the right there. And in this case, we're also doing it for like typical foams as well as the high solids foams. So we evaluated 3 extraction methods for analyzing PFAS and high solids foams. We knew that SW846 method 8327 worked well on typical foams based on our surface water research. From our findings, EPA 1633 performed as if it were being completed on biosolids for the high solids foams, performed similarly to our in-house protocol, SOP 3888, which is depicted here in the figure. 3888 is 1633, is it? Sorry. This comparison was done at a separate time. Both of those methods involved sequential solvent extractions followed by the solid phase extraction step for cleanup. And then our in-house method, SOP 3888, was compared to these 2 other higher throughput dilute and shoot methods, which include a modified SW846 method 8327, as well as an ASTM D8535-23, which was developed by EPA's Region 5 lab for soils and biosolids. So based on this data, there was less variation than expected across replicates, and the results were generally comparable between our in-house SOPs 3888 and SW846 8327. So in this section of the presentation, I'm going to discuss data from 2 utilities. The first utility serves 7,000 people and has PFOA at about 7 ppt and PFOS at 13 ppt. The other utility is a much larger utility, and I'll be primarily discussing this in the section where we talk about backwash. So this is the first utility in Tennessee. It treats less than 1 million gallons per day, but it has capacity up to 2 million gallons. The raw water comes from a reservoir, and it's dosed with sodium permanganate seasonally before chemicals are added. in the flash mix. And then you can see the water goes to the splitter where we found foam. This looks like a typical foam. And then after that, it goes to a flocculator where you can see we found some of the high solids foam. So in Tennessee, we had PFOS up to 20,000 parts per trillion in the foam, while it was only 12 parts per trillion in the water. And PFOA was up to 400 parts per trillion in the foam and 6 parts per trillion in the water. We saw precursors in the foam that were not reported in the water. And this includes PFOSA, MeFOSA, and ETFOSA. There were also certain PFAS that enriched in the foam more readily than other PFAS. So the utilities had many questions regarding the foam management, including questions like the ones that I've written out here. Are foams aerosolized when we spray them down? And is that safe for plant operators? If we land apply sludge from our settling ponds containing these foams, are we land applying PFAS? If we remove foams from the basins, how do we dispose of them safely, knowing that they contain high PFAS concentrations? Will the wastewater treatment plants accept them? So we hope that we'll be able to address these questions and some remaining research questions in the future, including investigating if coagulants and polymers enhance foam formation, evaluating the impact of foam removal, and determining if sites with foaming are suitable for foam fractionation. Okay, so now I'm going to talk about backwash. So we wanted to determine if there were elevated levels of PFAS discharge during backwashing, as well as evaluate the partitioning of PFAS between bulk water and particulate fines, and the initial implications of that for sampling and analysis, as well as the broader implications for residual management. So in this case study, we're going to discuss a utility in New Jersey, which is anonymous, where they installed Fluorosorb. They installed it in a filter before any additional treatment, which is unusual. They replaced the existing anthracite media, which avoided the cost of building new infrastructure in this full-scale pilot. So it served as a primary filter, but using it in that manner also decreases the lifetime of the media. Their filter was backwashed every 1 to 2 days, depending on the head loss and pressure buildup. And then during backwashing, you can see a picture here, foam is formed during the initial backwashing air scour. And I also include a picture there of the samples we took throughout the duration of backwashing, where you can see the total suspended solids decrease over the duration of the backwashing. So the results for the Fluorosorb filter are shown here, both without and with suspended solids removed. Figure C is the one where suspended solids have been removed prior to the solid phase extraction elution step. And you can see from this figure that there's reduced PFOS in orange and PFOA in black in the filter effluent relative to the influent in figure A. And that is the water that is used for the backwashing process. So the water that's used to conduct the backwashing had a composition of predominantly perfluoral carboxylic acids, while the sulfonic acids and precursors were present at higher concentrations in the backwash water. There were elevated PFAS concentrations observed at the start of the backwash cycles, but they decreased. So within about 3 to 4 minutes, concentrations are reaching the background levels. And this on its own may have implications for management. There's an opportunity potentially to divert water and considerations like that. So the early backwash had elevated PFAS in line with the elevated total suspended solids, and possibly due to some foam mixing. But by the middle of the backwash cycle, the PFAS content has the same profile or even lower concentrations than the backwash source water. There was elevated total suspended solids, PFAS, and PFAS, and the foam generation, which all seemed potentially linked to the air scour. But we're currently processing samples, trying to evaluate this, and we don't have the data to share at the moment with and without air scour. Just for your knowledge, the total suspended solids throughout the backwash process did decrease from about 600 milligrams per liter to less than 50 at 4 minutes and less than 10 at 7 minutes. And then here's a comparison that is quite interesting between the backwashing of the fluorosorb filter media and the backwashing of the anthracite filter media. And this is a unique situation where you can do a one-to-one comparison because fluorosorb is being used here and not being installed later in the treatment train. So the anthracite backwash contains slightly less PFAS, which may indicate minimal release of PFAS from fluorosorb during backwashing, or lack of fluorosorb fine particulate in the backwash water. Also important to note is that we've previously tried to extract PFAS from fluorosorb, and we've had trouble extracting PFAS from the particulates. So we think it's unlikely that desorption is the mechanism occurring here. There may be some consideration for sorption to other solids. And then this is the foam generated during backwashing. So you can see that PFAS were observed in the foam generated during backwashing. And the foam from the anthracite filter backwashing had lower PFAS concentrations. PFOS was reported up to 16,900 nanograms per liter in the fluorosorb backwash foam, and only about 3 nanogram per liter in the water. And then for foams generated during the air scour, which you can see in that smaller box, the proportion of PFOS released was greater in the fluorosorb samples. So in conclusion for backwash, there were elevated PFAS concentrations that were detected in the water leaving the filter during backwashing of the fluorosorb and anthracite filters. The PFAS increase was only seen during the first few minutes of the backwash cycles, which was indicating that there's an influence of the air scour and possibly foam formation. The sampling procedure and the analytical approach can definitely impact interpretation of the results, and studies should definitely consider this if they're trying to sample backwashing as well, including the timing of the sample collection, and may also need to look into confirming how PFAS are partitioning between the solid and aqueous fraction, and if additional sample preparation is going to be necessary to answer the particular research questions. AJ, how am I on time right now?
Yeah, you're past time, but you can. We're okay.
Are you sure?
Yeah, you should just go
Okay.
through your slides. It's fine.
Okay. So in this part of the presentation, I wanted to cover our piloting studies. So we know that full-scale PFAS treatment is a significant upfront and long-term financial investment for a community. So determining the suitability and the performance of a given technology at a given site is the best practice due to the complex and dynamic site-specific factors like the influent water quality and the treatment objectives. A treatment pilot is a site-specific technology demonstration at a smaller scale, which is highly predictive of full-scale performance. Piloting also allows for problems with potentially serious implications at the full scale to be identified prior to sinking significant capital into the full-scale treatment. Piloting treatment requires an investment of time and resources, though. And then also it's important to note that piloting requirements are established by the primacy agencies and may depend on the technology selection or the water source used, such as surface water may have more stringent requirements. And requirements may also vary depending on whether the state has deemed it best available technology versus some novel technologies. Our recess pilots often exceed 1 year, as the duration of our piloting is based on contaminant breakthrough data, as we'll discuss in a moment. So this is the recess pilot skid that I was referring to. This pilot skid was designed for easy transport. You can see it on the upper left there, wrapped up and ready to ship. We've designed it so that 6 media can be tested in parallel on each skid in a lead lag configuration. We've built in dechlorination with sodium bisulfite if needed, since chlorination can impact anion exchange resins. And then there is remote monitoring capabilities for things like flow rate, pressure, chlorine, and things like that. So you can see here on the pilot skids that I've noted where we have our chlorine analyzers on the lower left, and then where we have flow meters and sampling ports on the right. So briefly, this slide shows an example of breakthrough progression as the volume of treated water increases. I wanted to note that the EBCT, or empty bed contact time, is what we're going to use to represent the progression of water throughout treatment by the absorbent medias. And then taking samples at an intermediate sample tap can be beneficial. And I've put here like a 50%, 100% tap to use as an example. They can be beneficial since the progress of PFAS transport throughout the media can be tracked better that way, and it allows for the media usage rates to be determined sooner, so that comparisons across medias can be made. The pilot duration can also potentially be shortened, as obtaining complete breakthrough may take well over 1 year. And then I wanted to discuss EPA's water treatment models, which we use to describe the current analytical results and derive parameters that are used to project future system performance. If you're interested in knowing more about these, feel free to scan the QR code and or just look up EPA water treatment models. So the case study I wanted to discuss is at the same site in Tennessee where I reported the foam data. A pilot skid was deployed in January of 2025, and we evaluated 6 absorbent media in surface water. In this pilot skid, we are dechlorinating the influent, and you can see that I listed on the lower left there the different media that we tested, including Setco, Fluorosorb, as well as 3 anion exchange resins and 2 carbons. In this situation, the EPA fabricated and delivered the pilot system and provided ongoing operational support, which included the remote monitoring, weekly check-ins, replacement parts and chemicals, and provided analytical and modeling support. While we had the partner community help by running electric, running plumbing, establishing drain connections, providing access to the plant and communications, as well as daily monitoring of the system and helping with repairs as needed. They also did the sampling themselves and packing of the coolers. You can see the general water quality profile here. It's important to note the TOC is about 1.4 plus or minus 0.2 milligrams per liter, because that often can influence the modeling results. So this figure compares the PFOA breakthrough data for two different GAC media at the intermediate sample taps, with each figure being a different percent treatment. So you have 25% EBCT in the upper left, and below that is 50%, and then to the right you have 75 and 100% treatment. So in this case, both media are shown at each sampling point, with the UC 1240LD in blue and the F400 in green. In this case, it's difficult to visually discern removal differences between the GAC types for PFOA. And then here for PFOS, basically the same situation, but note that there's variable influent concentrations, and the influent ranges from about 10 nanograms per liter to 20 nanograms per liter. You can see here there is slightly better PFOS removal observed in the UC 1240LD, and you can tell that by the curve being slightly shifted to the right relative to the F400 curve. And then this graph shows the collected data plotted with the treatment modeling results for PFOA. The concentration is on the y-axis, and then on the bottom lower x-axis we have time in days, and then on the upper x-axis there's bed volumes. And you can see the point where the 100% breakthrough here exceeds the MCL, and we've marked that on the plot for reference. And then in the table, you can see our estimations for media usage rate there in bed volumes, or how many days it would take to reach that breakthrough point. And in this scenario, the UC 1240LD outperformed the F400 in PFOA and PFOS removal. And in this case, we would consider the change out to be based on PFOA and not PFOS, which is common since it generally breaks through first. And then for anion exchange resin, you can see a comparison here for PFOA, where there's breakthrough data for 3 anion exchange resins that are collected at the intermediate sample taps. CalRes 2301 is in blue, CalRes 2304 is in green, and PFA 694E is in purple. You can see that there were different PFOA removal efficiencies observed for 2 gel type resins, which I've underlined. The CalRes 2304 is currently removing PFOA more efficiently than the PFA 694E. We had to terminate the CalRes 2301 piloting earlier than the CalRes 2304 due to flow rate instabilities and pressure increasing. So you can see there that I have an arrow pointing to where we terminated its piloting. And then I wanted to show you the PFOS data, even though there's not a lot of it, for the 3 resins. You can see that there was different PFOS removal efficiencies observed for the 2 gel type resins, and it only broke through at the 25% EBCT for the Purolite PFA 694E. You can also see that the CalRes 2304 is also removing PFOS more efficiently than the PFA 694E. And then that's what this looks like with our modeling of the data. Once again, the PFOA will function as the driver of changeout. And we established that the CalRes 2304 was outperforming both of the other resins. it would exceed 1,000 days of use based on these breakthrough projections. And then I briefly wanted to include this lesson learned. This is an example that shows how important it is to get accurate media depth measurements throughout the operation of a pilot and not just at initial installation, as sorbents can swell or shrink after installation. In this example, you can see that updating the media measurements can improve the media use and cost projections. So you have the original measurements on the right, and then when they were updated, or on the left, sorry, and when they were updated on the right, you can see how much the predictions improved. Just some general takeaways. Piloting treatment can provide performance predictions and insight into site-specific conditions that can impact treatment at full-scale systems, which is important prior to investing significant capital into full-scale treatment. Ideally, treatment pilots should be designed to efficiently evaluate treatment goals and consider both the physical design and the duration of the pilot. Financial and time constraints may limit the practicality of piloting until sufficient breakthroughs observed at the 100% sample taps. So collecting data from intermediate sample taps and modeling results can generate projections and facilitate media comparisons, which otherwise might not be possible. You should also make sure that you're prepared for complications that could arise during piloting treatment, and make sure that you're tracking operational changes and communicating with technical assistance providers or design engineers. And generally just all treatment to work at all sites.
Clean them and stay clean. So the end
Tim,
result
hold on
really comes down to how
Tim, Tim McClellan, can you mute your line? Hold on one second. I'll take care of it. Oh, thanks, Tim. Good timing anyway. So Christina, thank you very much for the presentation. I felt it was warranted to give you more time because of some really good work there by your team that has not, to my knowledge, been published or shared. So I think it's super helpful to have heard that and to see the results. So thank you for presenting all that. And yeah, just from the commission standpoint, they've really valued the partnership with EPA, and really happy to have some technical support on some very difficult questions. So looking at the chat, I don't see any questions. If you have any, feel free to put them in there as soon as possible. If we don't get any questions, then I'm going to suggest we just go right into the recap of day 2. And again, thanks Christina and really everybody at EPA for all the good work that you're doing and continue to do to support utilities, large and small, to help with making good decisions. There's a lot at stake from a public health standpoint, and there's a lot at stake from a cost standpoint with these decisions. So not seeing any questions in the chat. I'm going to see if we I think Jackie's here and Christiana. Are you here as well? I see you're here. Great.
Yes, I am.
So why don't we jump into the sort of panel discussion and kind of a recap of what we learned. If people have general questions on anything that was covered today, we can also try to address those in the chat. We will wrap up at 2:30 as planned, so we will this will be a little shorter than planned, but I think that's quite all right. And I will get to the chat questions after we talk a little bit about. So one of the things that occurred to me as we're hearing all these different presentations is you have sort of vastly different approaches. You have Cape Fear, Passaic Valley Water Cape Fear already implemented GAC. Passaic Valley Water planning to implement GAC. Seems to be a common choice. But then you have some utilities that are leaning or headed towards powder activated carbon, Louisville water. And I'm just curious from the panel's perspective, if you have any thoughts on, the risk or benefits of those approaches. Like, is the pack option, and I should mention OWASA as well, is the pack option, does it have risk associated because you have this disposal question, and now whereas with GAC you're reactivating and that's not being disposed. So I'm just curious whether you see pack looking at those couple of options and how you might be thinking about those, because it's just interesting that some utilities are heading one way and others are heading another. And what do you make of that?
Well, a discussion that we've had, because we did the PAC study in Kentucky, and one of the things that we've talked about a lot is some systems may have a difficult time implementing that treatment type because they can't do any kind of process control testing. We don't have a benchtop meter for PFAS. You can adjust your PAC feed based on your TOC or your UV254, and you're making coagulant dosage changes based on turbidity and different factors. And we don't have that with PFAS. And so we do see a challenge there, especially for some of the smaller systems that may not have capabilities like Louisville Water. And I think I saw it with OWASA too, is having their own monitoring equipment on site. So, they can do that monitoring. But for the smaller systems, they may be feeding more than they need to at times, and other times they may not be feeding enough. So that's one of the biggest challenges that we've kind of talked about with feeding it.
Yep. Good point. Yeah, you don't have real-time PFAS results. You can make these fine adjustments to your dosage. Yeah. Any other thoughts on that, Christiana or Christina?
Yeah, I think there are so few treatment options we have, but there are so many different ways of implementing them, and that has to do with just a plethora of things. Like for me, one of the things is, what are the patterns of PFAS occurrence in my source water, right? Is that something that is higher in Q3 because of drought conditions and so on, and for the rest of the year we are under the 4 PPT range, and there's just the occasional Q3 hit where we may be over 4. In cases like that, I think PAC may be, even for us, a very valuable option to kind of get us through that, because those are also the months that for taste and odor we may be feeding PAC already, right? So there are ways of doing that in ways, or just to have a temporary solution in place before GAC can be installed, because we all know how long it takes, right? From piloting it to actually, establishing all the pieces that then can be used in full scale, right? That's a huge time commitment there. So for those places, I think PAC can be a valuable piece to the whole story. And like I said, some other places have decided to go PAC and use PAC for their treatment option, right? So like I said, different places do it differently, but there's so many pieces that go into the decision making on that, and I think we're just highlighting a few here, right? So that we could probably come up with a whole list there.
Thank you. Did you have anything to add to that, Christina?
I mean, I generally agree with both of what the other speakers said. I understand the idea of using it as a temporary solution. I'm hesitant in some cases to consider how effective it is, depending on the concentrations of PFAS in the water. If it really is a solution that's being used, for example, during 1 or 2 quarters, and you're trying to drop the PFAS level only a couple of parts per trillion, then that does seem to make sense as an approach. But I think that there are going to be systems where there are still infrastructure constraints or where the dosing possibly might not be able to be high enough to make an impact that they would like to see if using it as a temporary treatment approach. And then in that case, if you're still going to be investing in infrastructure and you're going to be needing to conduct piloting, et cetera, it may not be as practical as it initially seems.
Yep. Yeah, good comments from everybody. So related to this, Amanda asked, so for places that have their own labs on site, how fast can systems get results? And is that enough time for operators to respond with PAC? So that's a really good question. I'll add from my experience working with the commission, and they're also hesitant to promise what could be really taxing on the lab staff, people like Liliana there. But they've been promising about 3 days that they can turn the results around, which is great. And if you're monitoring your source water and watching for trends, you're going to start to see things change. And I think getting a sense for how quickly the levels can change will be helpful, because I think our sense is that you're not seeing really drastic changes. You're seeing changes over time. And as long as you have enough time to react, then you have plenty of time to increase a pack dose, for example. I do think most utilities will err on the side of caution and not try to dial in the exact dose, knowing that they don't want to underfeed and then have a violation or a compliance issue. So that would be my take. I don't know if anybody else on the call has experience with that as far as how fast you can get results if you have your own analytical testing, and is that enough time?
I am an analytical chemist by training. The current PFAS testing results, especially the ones that are required for compliance, like method 533 and 537.1, can easily take 2 days of just sample preparation. So that significantly constrains how quickly you can get results. But depending on the sensitivity of your instruments, if you could get away with using a direct injection result, in that scenario, you could get your results quite a bit faster.
Great. Any other thoughts on this one?
Analytical chemist here, just wanting to highlight what Christina just said. We did build in at American Water a direct inject method to have a fast response time whenever needed. I think the other piece that AJ, that you mentioned, that I just want to get back to, whether the drastic changes in the source water, and it can happen. So this is why I think it is really, really important to understand what your triggers are. If your trigger is a rainfall, and a rainfall can, under some circumstances, actually increase the PFAS in your source water. We have seen it in our systems, right? So you can have that. So understanding either where your PFAS is coming from or what changes you could see through the seasons is an extremely important piece if you want to rely on PAC there. So the more surveillance one can do even upstream, the better it is.
Yeah, that's a good point. And another example of where you can't universalize some of these things. So for the commission with a reservoir, it is slower, but with you having a river supplies, the changes can be faster. So that's a good point. I did want to just bring up something related to the fluorosorb, because we did talk a lot about it. There's been a lot of interest in it. It seems like it could be helpful for some utilities, given its characteristics. From the commission experience, I think some of the things that were discussed were, are there ways to improve the settled water quality to reduce the amount of, for example, manganese or aluminum or other things that are creating problems for the fluorosorb, and also the concept of potentially adding that sacrificial layer above the fluorosorb, and using that as a way to sort of protect and prevent the fluorosorb. Yeah, allow the fluorosorb to deal just with PFAS, like basically use the right tool for the job. And the other thing I've been thinking about related to disposal, because we're all concerned about disposal of this media, we have heard and we have seen that it's very hard to remove PFAS from the fluorosorb. We can't even with we're trying with acids and whatnot, we can't seem to extract it. So it seems from that standpoint, and I don't know how much testing's been done with like TCLP and does it leach, and but to the degree that that media would not may not present a problem at a land application, makes it also sort of interest. So I'm just curious if you had anybody on the call had any thoughts about, you know, those aspects of fluorosorb. And if not, that's fine. It's just observations I made, and if there's really no other reaction, that's fine. I'm curious from we have only about 8 minutes left, so I'm just curious if there are any other takeaways that you either from today or yesterday or in general that you think yeah, maybe, you know, high level, what do you take away from all of this information? What would be valuable to people to walk away from with?
To me, there's not one size fits all type of approach, right? Like I think we've seen it. We had 16 great talks on PFAS, and everyone highlighted different pieces. Every talk highlighted different aspects that were important for the system itself. So getting to know the water source, where's the PFAS coming from, understanding what treatment may fit best, and then trying it out before you go into full scale, like piloting. I still find piloting one of the very important pieces to it, to really make sure that you don't have a rude awakening once you get your full scale plan going. Right, to know that what you can achieve with that, I think are for me at least some of the aspects that we're trying to look into for each and every plant that needs PFAS treatment.
Jackie?
I agree with that wholeheartedly. And I also think, you know, we've all just been forced into this, right? And we're just kind of learning as we go all together. So to me, it's just interesting to see, you know, we have the known technologies, but it's also interesting to see the creativeness that's coming out of this from all of these really smart people that are working for these solutions. But, you know, there is that with us being under that time crunch, and, you know, and we've seen it in Kentucky with most of them going with GAC. It's a known technology. They know it will remove the PFAS. There's some extra benefit to it. And I think it'll be interesting. I think we need a few more years. I really do. I mean, we don't have that with drinking water, but I think that in the years to come, as we see limits be put on effluent discharges and those sorts of things, I think we're going to see a lot more technology come out that's available for destruction and that sort of thing. But I think that with drinking water, we're, you know, on the cutting edge, and everybody's doing the best that they can do with the knowledge that they have. So.
Great, thank you. How about you, Christina? Any other final thoughts?
Yeah, I mean, I'm trying to think about what I should be saying here, but generally, most of these talks had me pretty excited. It seems like a lot of people are considering very comprehensive approaches. Originally, I was concerned, not necessarily like during this webinar, but previously, that there was a lot of one-size-fits-all solutions that were trying to be applied. But now I see that there's a lot of dynamic thinking, and they're not just thinking about treating the water itself, but considering residuals and what to be doing with them as well. That's incredibly important because we don't want to create additional problems down the line, for sure. But on a standpoint for my research and my research initiative, I'm just thinking about the opportunities here to combine potentially all of these case studies and gain some of the lessons learned in a way that could benefit people on a national scale. And I'm really glad that you organized this.
Great, thank you. Well, with that, we'll conclude the recap. Really appreciate the help here from Jackie and Christiana and Christina. Thank you so much for sticking around for the end here to do a little recap of what we heard and learned. Really enjoyed the entire seminar. Had a lot of fun putting it together. Some really talented people in our industry, all really focused on public health. You know, how do we solve this challenge for the people that we serve? And great to get different perspectives. Some leading researchers from consulting firms. We had even some folks from academia. We had regulators. So really good cross-section, utility folks, cross-section of people dealing with this. And yeah, really hope it was meaningful and helpful to all of you who participated. We will be compiling some video, a couple of videos from each day. We'll put that up on YouTube. I will share that. I have to check on whether or not the slides are people are willing to share those, but if they are, we'll make those available in some fashion. And what else? Yes, just I guess stay tuned for follow up. I do want to get some feedback on what was valuable and what you think we could maybe dispense with. So stay tuned for a little survey of some kind. So that's a wrap. Thank you all for attending. Thanks to all who are still here who presented, and hope you have a great rest of your day. Thanks, everyone.